All right, let's get going, why don't we? Hopefully it loads into the right computer right away. This looks correct. We've got our little address translator here. All right. So first things first, I need to fix up the jump instruction, which is right here. All the jump instructions need to be fixed up. Let's see. What these instructions need to do is they need to read the next. Okay, we need to get PC +1. Why is this adding 2 to PC? This should be adding 1 to PC. Yeah. That's what this up here does, right? Okay, which of these registers is PC again? There it is. Okay. Sublime. PC is register 4. So 0, 1, 2, 3, 4. This is PC. You have a delay line. Yes, we're adding 1 to PC. On every clock step. Otherwise, we're adding 0. Alright. So, we do indeed want to add 1 to PC. That's one small bug fixed. Actually, no, we want to add 2 to PC. Because in this particular step, we want to step over the next memory location. We also want to add 1 PC. That's for a different reason. What are we accessing memory for? Okay, we're storing something to memory over here. Okay. Oh, we have call and halt. Yeah. So call is pushing stuff to the R stack. Okay. Well, we need to move these out a little bit. I do believe. Hello, Dread. Completed a few more quests. No. I need to do more questing myself. Oh. Wait, do I actually want to move this out? Think for a second. Anyway, which ones did you do? Any notable ones or just a bunch of random stuff? Okay, so I need to add 1 to PC, and I need to request that from memory. In most, but not all cases. Namely, all of these cases. I think I want to move this whole clump outward. Okay. We'll just move it to there for now. All right. Yep, we're still doing Turing complete, Colo. For a little bit yet, at least. Okay. We'll add 1 to PC. And then I need to put in some OR gates over here. I do believe all of these, and actually this one as well. Okay. Boom. Oh wait, I should have placed another one. There we go. Okay, if this line is lit, then we are doing something that involves a jump. Like call involves a jump too, doesn't it? The only one that doesn't is halt. But technically this one should also be tied into the OR fun. I think. Yeah, possibly. Yeah, because call is just a jump with a push. So we do need to... Let's see, is this the call? Yeah, because this is halt, so this is call. Okay, this is mildly inconvenient. Actually, I can just do this. That's probably going to be more compact than anything else. Alright, now... that's a lot of OR gates. So this is going to control if we request the next cell of memory. Yes, which we should be able to do. We'll run this straight onto the memory load line, which I just realized is not brought across right now. Okay. Oh. Okay, so memory load. Also, I can't just hold this high, so we need to use a diode. Okay. Now, wait, that's wrong. There we go. Now, I need to Also, put in a switch, a 16-bit one. I need to move this diode. I'll put it out there. Boom. And this goes to... shit. Okay, this is going to get in the way of call. Because call needs to do a store at the same time as we need to do a load for every purpose. I think we're going to have to change the semantics of call to use a return register. Better go do that before I forget. I better document it right now. Okay, so we do have an empty register right now. Register 7, or aka bank, is now known as register RTN, or return, and is used for the return address. And I need to add another instruction. We'll add it between call and halt. We'll add ret, return, which will, here, we need to change this. Copy PC to RTN, jump to immediate argument. No. Yes. Copy RTN to PC. That's all it does. Just copy return to PC. Okay, we won't actually add that instruction yet. We'll think about it. Because we can just do anything that'll end up with PC pointing to the return address as a return. Okay, we do need to go modify the ISA to fix the call instruction. First off, we need the address line, but we no longer need the address line for this. We can delete most of the fancy bullshit for the call instruction. Memory value is not needed because we're not setting memory. Memory store is not needed because we're not storing. Overflow is not needed from there. But we should add the overflow from there. Don't know if that's a good idea or not. I need to completely redo calls encoding from the ground up. Because really call is just exactly like jump. This part right here. With the addition of a copy. And we'll be copying result V, I think. No, we can't copy the result V because that's going to PC. Are we gonna have to write a special, draw a special line? Talk to the bank, not bank, the play. No, let's see. Return address is right before the frame pointer, and right after the stacks. This right here is the return address line. I think we need to add a special out-of-band set for the return address. Because we can't set PC and return address in the same, where I'll call it. Okay. Go ahead and make a little pin here. And then we need an RTN set line. Which I should have drawn first. Okay. We're no longer doing anything stack related here. We can cut that off. Okay. Now. We can cut this off. Alright, let's go and code the call instruction properly. Which group is this? Group 4A. Okay. Call takes register 4, aka PC. Source register 4. Takes an offset argument, which should be immediate. And let's see, register 6, that's a bank register. We don't actually need that anymore. Okay, and it implicitly uses as an argument PC plus 1. But we have to load that manually. Jump does the same thing. Fix an immediate. I'm gonna have to go fix all of these, aren't I? Okay, 4B. Yep, all of these have to be changed back to being immediate. Okay. Additionally, I need to go make sure the jump code is handling this case properly. Argument 3 is not being used at all. Oops. Except in the case of halt. Okay. So argument 1 is the current value of PC. Argument 2 is a constant offset that is being added to PC. 4 jumps. And this should no longer be in use. Wait a second, let me think about this. Okay. This is getting the address. This needs to be attached. Shit. Okay, we have a huge problem here. The memory read code puts its value on result V. We are writing PC, the new value of PC, to result V. Those two things can't be allowed to coexist. So we're going to have to move the new value of PC directly into PC somewhere. I guess we're going to have to move that over to the secondary bus, which is becoming a little bit more official than I would really like. Damn it. I know better than that. Okay. And then we have a override PC value. I can come in as well. This doesn't need to have a switch. And this is not correct. This was never correct. Doesn't really matter because the only other instruction in here is halt. We should be using this value though. That's better. Okay. I think that's better anyway. Well, this is high. That means we're setting PC remotely. which means I should force this high. Okay. In this case, I need to decide between this or this based on this value. They need another multiplexer. Okay. Wait, can I just draw this straight down? Yes, I can. Good deal. All right. Sorry, survey. It's only going to get worse. Oops. Because later, we're going to be dealing with this. All 1100 lines of it. Don't act too excited. All right, so I don't remember which leg of the multiplexer's on. Okay, it's the outside leg, which is exactly what I want. Good. All right. So we should, in theory, have a way to override PC. That is not addressing it directly, which means we also need to go through and unaddress PC and readdress it to register 7, aka the return register. So let's modify 4A. Okay. Jump and call are both changed. Actually, no, wait. Call is changed. There's call writes to return register. Jump needs to be changed to not write to anybody, because they have their own back channel to PC. Yeah. Okay. And now 4B. Now, oh, now the jump instructions should be fine. We don't actually need this back channel to return after all. Wait a second. We do need a back channel to return, and I need to go fix call. I forgot, the memory access we have to do has to come in on that line. That's why we had to have a back channel to PC instead of just replacing it. So this must be 255. All jump instructions absolutely must not have a return result. Because we're getting memory access in on that line. Yeah. Because we're doing a conditional set from result V to PC. But we can't use the normal mechanism for a set because it's conditional. So it has to use the PC back channel. Okay, so this is the return back channel, which call uses. All right, first things first. PC plus 2 is what happens if we don't call. Wait a second. Oh, that's wrong. We want to do the memory load in all cases. So that goes from here. We want to do this increment by add together an increment by 1 only for oops. No. There we go. This step only happens for call instructions. Because this adds PC plus offset, stores them together. Call doesn't do that. Call takes wait a second, is this right? No, it isn't. Yes, it is. No, it isn't. Because we don't take the current PC and add an offset to it. We take the memory value and add an offset to it. So that means we need result V right here. No, this is right. No? No, it's not right. What? Yes, it is. Because we take PC and add 1 to it, that's the memory address that we want to read. Okay. And that will come in on result V, which will then go through the multiplexer here. If we're supposed to jump. Okay, if we are supposed to jump, we will take the current memory address that we just read. We'll read the memory address in all cases. And it'll come in on result V. Okay, I think this is right. Am I missing any steps? Possibly. Yes, I definitely am. Because we're not setting the return value for call. Okay. PC. We don't have to have the call return value set over here. Question out would be more convenient to have it over here. Okay. That'll do. I almost should just rig the whole call instruction up on this side. Nah. We'll leave the basic part of it over here, but... What is this even used for? This is PC plus 2. Which I think was used by call for something. We don't use it anymore. Anyway. Now I can make this more compact if I move that up. Okay. That'll work. Gonna leave a little bit more space though. Alright, now. Actually, we want to store PC plus 2. We want to store this, not that value. We want to store this value. Instead of that one. Like so. If we're doing a call instruction, we save PC plus 2 as the return address. Okay. I think our jump problem is solved. Now we have to test it. And for that, we're going to have to summon an old friend. Sublime text. Okay, so to test this, I'm just going to write something really, really simple. Here. Let's just write a simple but actually functional program that counts up by 1 every time. Okay. We'll load 0 into the A register. We'll increment it. And then we'll do an unconditional jump back to the start. And then I'll just pull up a console window. I'll run my little translator program. And we go over here. And that gives us code. Paste into there. Okay. It's not doing anything that it's supposed to do. Why not? What in the world is going on? Okay. Here we go. Here, let's actually have it load 5. That way we can see something happen. LDI is not even working. What? It's not energizing the store. Energizing the store for PC, for LDI. What in the hell is going on? Okay. For some reason, it's not properly energizing the argument constant. How did LDI get broken of all things? Let's see, this group's 0, isn't it? LDI. Argument 0, constant. Store to 0. Argument 1, I mean. That makes 0 cents. Did I never fix the encoding? I must have never fixed the encoding. Add boot. I swear I did, though. Yeah, boot's not in the list. That's weird. Okay. Well, this is boot. That's LDA. That's LDI. Let's see, what other things were in that group? LD high. STA. And SCF. Okay. Nope. Well, let's see if at least LDI works. No, what is it doing? Boom. What instruction is it decoding? Result select is 4. Okay, 33.5. 33 would be... Wait. I just encoded all those instructions wrong. Boom. These are group 0, not group 1. Sure how this happened. I swear all these were encoded correctly the first time around. Okay, LDA. LDI, LDI, STA. What is that? And SCF. Okay. Not right at all. Here's LDI. That's right. Why is it not loading the right thing then? Okay. Go ahead and encode there. That should be LDI. Yes. Yeah, this should be the same instruction that's coming in. 32.5. That is indeed energizing LDI. Energizing arg1 const. arg1 select. Unless I somehow got op and arg reversed, which would be a bit insane. I think I did. Op is on the bottom. Wait. Okay. I swear all this stuff worked last time. Okay, we just executed the boot instruction. Okay, wait a second. So this should jump us into program memory. Wait. This is not correct. Or is it? No, it's correct. Boot's not. What is going on? This should take PC and multiply it by 2. PC should have the high bit set if it's executing program code. Otherwise, it should be executing from RAM. And for some reason, I don't have the switch here that's supposed to make all this work. Yeah, I do, right here. No. No, I don't. Yes, I do. Because this will index the program, but it won't do anything. Okay, the reason nothing's working is because we're executing the boot instruction over and over again. I need to change boot. Here. Boot is instruction 0, group 0. I change boot. So it writes to PC, which is 4, which is how it works. Yes. Okay, I see. I screwed the boot instruction up somehow. But I'm not sure how. Oh, I do too know how. This isn't working. Okay, this is supposed to be writing this 32,000 whatever value to PC. It is not doing that. Because I have that diode backwards. And this diode backwards. Do I have any other backwards diodes? Doesn't look like it. Alright. Okay, now the program counter moved. Okay. Now we're loading up stuff. Okay, it's rebooting at the end. But it's not actually... Okay, this is the boot instruction. There we go, LDI. Increment A, which works. And this is supposed to be jump. Is GMP somehow not encoded? There's no way, because it's showing up highlighted. Group 4, okay. Instruction 0. Okay. That should do. Why does it make that weird tick noise? Okay. This is the increment step. Register 0 should be 6, yes. Okay, so the next step is supposed to load the next value from RAM, which is 40. Okay. And the next value oh, I see what the problem is. How could I miss this? Okay, so program is not fully addressable. Do you see the problem? Where do the address lines come in for program? From PC. None of the memory access lines connect to the program block. The program is addressable only during the PC load cycle. It's not currently uniformly addressable the way it needs to be. So, I need to rig it so that not only can we access it during the program access cycle, we can also access it during the data access cycle. Because we need to be able to read our ROM all the time, not just some of the time. Which is mildly annoying. We want to use the same address translation layer. Basically, we just need to connect up these wires to this, ignoring the right stuff. So we don't need memory V, we don't need memory store. Those two don't work for ROM anyway. We do need memory load and memory address. So, we need a 16-bit mux. I do believe. If we plug a 16-bit mux in here, and hook this to the clock wire, it'll read either from PC line or from the memory address line. And then we just put a switch based on memory load, connect the output to result V. It should be that simple. Okay. We need a NOT gate on this. Boot. Boom. Here we need clock to be low. Copy it over. This clock low means we're reading program. Here. We load the boot instruction. We write PC. We load the first instruction of the program. We load any memory it may use. Okay. And then this line next to address. And it doesn't like that. because we don't actually need this to be on this line. We need to be on this line. Or rather, this part of the line needs to connect directly. Well, here's an easy solution to this problem. Okay. Just select that as well, so we can just move the whole thing as a block. We need to go down 2 blocks. Come on. Okay. Now, that connects to clock. And that connects to there. And it still doesn't like that. Oh, how do I fix this? How does it think it's cross-wired this time? That doesn't make a whole lot of sense, actually. Yeah, it's not smart enough to realize that just because it's running through a multiplexer doesn't mean both of those wires can be on at the same time. Damn it. I bet you if I disconnect the control wire and just replace it with an always on bit, it still won't make any difference because, yeah, multiplexers are bugged maybe when it comes to proper handling. Oh, this is gonna be annoying as hell. Okay. How do I deal with this? Okay, it still doesn't like that. All right, let me think about this. it doesn't seem to realize that there are two cycles. And different things are on during different parts of the cycle. Because, yes, during the first tick of the cycle, it will be reading and writing in such a way that it could set address. During the second tick of the cycle, it won't have anything to do with the ISA. I have this wired wrong. Okay, let me think. This will only be on when the clock is ticked high. Which is backwards what it's supposed to be? What? Clock high means it's executing, not that it's loading an instruction. I think. That still doesn't work. Like, even if I unwired this, it would still say that there's a short circuit through that switch, which is impossible. Because if that switch is never high, then this can never write anywhere. Yeah, that's insane. Like, yes, it could, in theory. If it wasn't for all the reasons why it can't. I think they just have bugs in their circuit dependency checker. Oh. How do I resolve this issue? Because I need to be able to read we're gonna have to go to the program bootloader method again, aren't we? No, that won't help anything, I doubt. Well, maybe it will, but... Okay, basically it's saying the obselect can energize this wire, which would lead to this wire being energized, which would result in determining the value of address. Okay, but there's a problem here. OpSelect cannot be active Okay, I think I know what I need. Oh, I know what I need to do. Yeah, okay. The reason why this was hooked up like this is because we weren't doing the delay line stuff we were doing over here. We need to do this delay line bullshit. So I need to make some space. Okay. So when this line is high, we should allow a value through from this delay line. Hello? What the hell? We don't have the output of this hooked to anything. What is being... Yes, I know how that works. But what output of what component do you think is simulating or... Okay, it's basically once again saying that this switch is the root of the problem. Or one of the roots of the problem. And that somehow OpSelect being able to set this switch, but OpSelect is set what the hell does it think it is doing? There's no connection. There kind of is. Because I can say address. But it's based on the clock. And this doesn't write to anywhere. Yet. Okay. So if the clock is high, which pin is selected again? I can never remember. Okay. It's the outside pin that's selected if it's high. So if the clock is high, address goes into this thing. It comes out here. If the clock is low, then we use PC instead of address. And if the clock is low, then address has nothing to do with this, you piece of shit. All right, let's try it with a switch. We don't even have to connect a control line up, and it still thinks that somehow address is controlling. Yeah, that's insane. This has got to be bugged. Although actually, here. We need a 1-bit delay line on this, I think. That's right. No, it's not. Yeah, it is right. Yeah, it is, because 1-bit delayed. Maybe? Okay, the clock is low. Yeah, I think if we think using a delay line here will solve this problem. Technically, we should be able to do, actually wait, we should be able to do that and have it work just as well, but it refuses to allow that. We can do this and it should work, which is insane, by the way, but oh well. Okay. Now, this needs to either go to result V or to the delay line based on the value of the clock and based on the value of memory load. So if the clock is low, then we go to the delay line. We decide later if it gets out of the delay line by using this. But if the clock is low and we're reading a value, it goes to the delay line. If the clock is high, we go to, what do I call it? Oh, If the clock is high and memory load is energized, means we probably want to do this a little differently. And memory load is energized. And the address selector says so. Means you really want to do this differently. This is the address selector. There we go. Need a 3-bit and. Then we write to result V. Okay, this darn well better work. Pick. Okay. This should load 5. Yep. Pick. 6. And this should, next tick should energize the jump. That was not a happy sound. Okay, what exactly was the problem here? Okay, now we just ran LDI. What? Okay. We just ran increment A. Oh, is that ticked because it reached the end of... Let's add another instruction on the end. It reboots. What? Okay, run the first instruction. Okay, this is loading the jump instruction. Just group 4, instruction 0. And that is executing the jump instruction. Okay, jump. The value that is coming in on result V is 0. That is not what it's supposed to be getting. Supposed to be loading address 3. This is loading address 1. Okay, what's the value of PC right now? Is it even selecting PC? It is not load selecting PC. What the hell? Did it not increment the program counter? Okay. Boom. So it's 8001 right now, which is correct. Now it's on 8002. Boom. And the value we're getting okay, the jump circuitry is energized. Energizing the jump instruction. Jump conditional is on. But it's not loading PC. ARG1 should be set to PC. Why is ARG1 not set to PC? ARG2 select is set to 0, constant. ARG1 select is set to FF. That is definitely wrong. This should be set to 4. How did that get set to 255? I better check 4B to make sure that's still set up right. And the game just crashed. Alright. Group 4B. Yeah, they're all set to correctly load 4. Okay, for some reason, I must have just screwed up 4A. Double check, make sure it's saved. Yep, okay. Alright, let's try this again. On the anchor mat. Address larger than size of RAM. Okay. That is okay. It's obviously wrong because the address is not supposed to be getting through here, so we need to make sure that we're switching things the right way. Are we just switching on clock and not based on this? I bet. I do believe we are. Okay. So this needs to be based on clock and the high bit. Yeah, like this one is already doing high bit shenanigans. Why am I doing it this way instead of just using a bit indexer? Sometimes it's better not to ask questions. Probably because we want to strip that high bit off. But we don't actually, because yeah. We straight up don't want to access RAM when the high bit is set. This is becoming a bit of a rat's nest. And I probably should have done it correctly from the start, but oh well. What would be the easiest way to retrofit this? Okay, so for the store line, I think the easiest way to retrofit this is just to disable the address input here if the address's high bit is set. There's no easy way to do that in here because it's too tight, too compact. I could move things farther apart and fix it up a little bit. Like that. Okay, that's a bit unfortunate. A little bit better. Indexer. This needs to be before the switch. Oops. That's a byte indexer. I need a bit indexer. And this needs to access bit 15. Okay. And I need a NOT gate. Basically, if bit 15 is set, don't do the thing. Short circuit. Of course, I need to apply the same kind of logic to this output. There we go. I better believe it'll work. Should work anyway. I need to invert this again. Basically, this will say to output here. No, it needs to be like this. If the high bit is set, then don't output there. And this is already rigged for that same high bit check, which I'm going to actually remove from over here, because this is a very non-compact way to do that. Oh, this needs to be off PC. Of course. But a different wire. This wire right here. Actually, I can do it to the multiplexer output. No. That's dumb. Where am I going to run this wire? Like that, I think. Address larger than size of RAM. Alright, this check needs to be after. The switch needs to be after the MUX. means ideally, I'd like to move this mux in. Okay. Now, wait, what am I thinking? After the mux, not before the mux. Okay, now. This needs to be bit 15. Connect that to the switch. For an inverter. Okay. Now the mux is set by clock. And that's it. This turns address on and off based on the clock. Into this. We'll go there. This needs to be after the NOT gate. Means I could cut out a bit of screwing around there. And then this switch comes on if this needs to be time delayed by 1 tick, doesn't it? Yeah. Because it needs to match the delay here. We could technically invert it and get the same result because it's a clock signal. But that won't work here. It will just complain about short circuits. Oh. Actually, this isn't a clock signal, but may as well be. Okay. LDI is just executed. Increment A is just executed. And it just did something weird. Okay, why does it do that? What is it complaining about? Like, it's making that different tick noise that indicates something went wrong, but what? It doesn't give any hint that, and that just boot loops. It gets a 0 instruction. Alright, let's watch the outputs. Okay. Here it's executing increment A, which if we check, should indeed be the case. Yep, it just finished executing increment A. Okay. Now, it's loading jump. Okay. And now it should execute it. So, we're asking for register 4, aka PC, instruction 4, aka jump, with a constant argument of 0. Okay. We're asking for memory address 32771, which is being interpreted as 6. Which should be this should be 02. Means we need to fix the assembler, but that's beside the point. Increment just ran. Jump just didn't run. Okay, we're asking for memory address 6. So this should be, okay, this is 0, 1, 2, 3, 4, 5, 6, 7. So it's asking for OX80, OX02. What it is getting is not that. Zero, 1, 2, 3, 4, 5, 6. 128, 2. Boom. All right. Why is it not getting the right memory value? Okay, so it's trying to load 6. That's exactly what it should be trying to load. And we should be getting 128 to... Why is it loading 640? Okay. Oh. It's got the bytes swapped. Does this thing use Little Indian? Okay, why is it... Execute increment, execute jump. It just goes tick and starts over. Three, 2, 7, 7, 0. That's going out in result V. That should be stored in PC. This is flags. This is PC. PC is definitely being right selected. Except it isn't. I think I have that backwards. Okay. No. Um... Oh, this was never hooked up. Is that the right thing to hook that to? This was unhooked at some point and then never rehooked. This is the switch that says a jump is... This should be hooked to the same switch as the same control wire as this is hooked to. I think. Okay. This is not being disabled properly. What? There's a gate just missing right there. Going to take every time, which you didn't do before, which let's go figure out. Increment. Jump. Jump. Change that back to what the assembler had originally. It's working now. Okay, so the assembler was right in the first place, I think. Got another instruction here. Okay, this should not change this jump offset. I'm not sure what that weird tick means, but it happens every time we jump. A is definitely being incremented, as is R0. Okay. I think jumps probably work now. And we don't need to make any changes to my assembler after all. I said assembler. It's not really an assembler. It's very janky code that sort of works if you squint a little. Actually, wait, we do need to reverse that byte order. Alright, let's go do that right now. Okay. In fact, let's go look at this very janky code. There it is, less than 100 lines. Making extensive use of search and replace. Cranked out at 4 a.m. in the morning. Not exactly my greatest work, let's put it that way. All we need to do to reverse the byte order is just go ahead and change this. Instead of saying low high, or saying high low, it should say low high. And there we go. All right. So, let's try a function call. We'll just do increment R0 inside the function, and then we will do okay, we really need a return instruction. The problem is, it doesn't make sense necessarily. Okay, every instruction needs to be 2 bytes. That's how it's currently set up. Every single instruction is 2 bytes. Trying to change that would be incredibly difficult. To do 2 bytes, you need 2 tokens with the way the current setup is. If I actually wrote my own assembler, we wouldn't have to do that, but I didn't because I did not do it when I planned to do it. Instead, left it to the end of the week and then scramble, 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 get it done at 4 a.m. So instead of writing an assembler, I just wrote a very simple address translator or a label translator. So we don't have niceties like just not having to provide extra arguments. And instead of outputting binary code, we output text that gets turned into binary code by the game. Which is not ideal in a lot of ways. But this does mean if I do a return instruction, I'll basically need to provide a dummy instruction, or dummy argument. Because all return has to do in this architecture is copy the RTN register to PC. So I could write return as 2 instructions, but then I would need to preserve A, and I'd rather not have to do that. So I think we're going to do return as its own instruction. Which means I need to define it. Oh, where should I put return? It should go in group 4. It should go right after. It'll have a meaningless argument. 50 days in a row? Well, I guess I'm proud to have wasted your life 50 days in a row. Okay. Also, I need to define the RTN register in here. And I should go ahead and define ret as well. Let's see, that is group 4 instruction 2. So group 4 instruction 2. And then halt needs to be redefined because we're moving up one. Come on. They're in alphabetical order, you idiot. Can't be that hard to find them. There we go. All right. Now, Group 4A. Okay. That'll be return. It will take as arguments register 7, and as destinations register 4. And it will ignore any other arguments it may receive. Okay. I'm tempted to add a little tiny bit of code to automatically insert a dummy instruction. I don't have to type that out. Nah, we'll do it later. Or maybe never. Probably never. This is now the halt instruction. And then this little chunk of code right here is going to go ahead and copy arg1v to result v, like that. And that should be all that needs to be done. All right, now back to our assembler. Assembler. We just do ret 0. We don't need to preserve any registers here. Okay. And then we just do call 0 increment. Okay, you know what? I am going to go ahead and change the assembler a little bit. Okay. Search for call replace with call underscore. Search for ret replace with ret underscore. I mean, I just have to define underscore as being equal to 0. Yeah. And that way we can have single parameter. Let's go define underscore right now. Okay. That should work. Now, back to our regularly scheduled text editor. Sublime, are you feeling okay? Yeah, there we go. That was weird. Oops, this is the wrong one. Wonder. Okay. Yeah, who cares? It'll be overwritten in a second anyway. Alright. We'll call increment 5 times, then we'll halt with 1. Alright. Go ahead and bring this up. Run the program. Okay. Paste our program in. And we run it. And I'm pretty sure it's not doing what it's supposed to be doing. That value is not what I wanted right there at all. And why did it store anything to R? Oh, it's incrementing R0. It's supposed to be incrementing A. Okay. But more importantly, what the hell was it even doing? How was it writing to A in the first place? Okay. Yeah, call is definitely not functioning. It's writing to the return register, but it never actually jumps down through here. Okay. Go. We should have just executed LDI 0, which indeed it does look like we are doing. There, we're loading the call instruction. We execute the call instruction. Okay. So we should be doing a jump to not where it is currently going. What in the world is it doing? Here, let's restart. We just executed the boot instruction. We just executed LDI. Here, let's actually change this to 5 so that we can actually see it do something. We just finished executing LDI. Now it's loading the call instruction. Executing the call instruction. Call is not properly doing anything useful. Call should just be a standard jump with a few sprinkles. It clearly is doing something different, though. It's energizing memory load. It is not energizing memory address. Why do I have it specifically set not to energize memory address? Oh. That's because this is wired wrong. I rewired this half when I added rat. I didn't rewire this half. Basically... No? No, that doesn't make sense either. Why was this ever different? Call is another unconditional jump. I think this should fix it. I wish there was a button I could press to just automatically select the program block and open its editor. Okay, LDI has been executed. Call is loaded. Call is executed. It jumps to the wrong place. Okay. I see. I think I know what part of the problem is. I need to move these up above the parser block for starters, because that's going to throw off our count if we don't. And also... let's go ahead and run the program again. Okay. Let's see. This is in no way correct. The offset. And I think the problem is it's not properly adding. That might be some of it at least. Because this value is completely wrong. Because this... Okay, what is the assembler doing here again? Okay, first we're splitting the whole thing into tokens, one line at a time, because that way I can drop comment lines easily. And blank lines, because we don't care about them. And then I split each line into fields. In other words, space or other white space separated elements. And I get a list of all the white space separated elements, because we don't care about that are not comments, basically. I should actually be checking for end-of-line comments as well, but I'm not right now. End-of-line comments aren't allowed. Then, I go through it again. Oh, and I make a list of all the labels that are in the code. But I notably don't do anything to them, I just pass them straight on through. And then I go through and I count how many bytes the program is going to be. So for each element, if the element is a recognized label name, then we add 2 to the byte count. Otherwise, if the element is prefixed with a colon, in other words, if it is a label definition, then we don't do anything, except set that label's value to our current byte count. Which we maybe should do byte count plus 1. We probably should do byte count plus 1. The current situation seems to be working though, so I'm not going to mess with it. Or at least this does not seem to be our problem. And then if it's not a label, and if it's not a reference to a label, we just increment the byte count by 1 and go on. Because otherwise every token is 1 byte. Okay. Then when it's time to fill in the labels, we separate the high and low bits. And we mask in having the high bit set. Refer to a ROM address. And then we replace the original label definition in the original input string, not the parsed input string. We replace the original input label definition with a comment. And we replace uses of the label prefixed with a space or a tab, because that way we can differentiate it between the definition, which is prefixed with a colon, with the bytes, the byte pair that makes up that label's address, together with a comment that specifies where that label goes. And then we just write that result to a file with minimal error handling. Let's see. This should be working. I am going to write as part of the comment. Why am I dividing it by 2? I'm counting bytes. That'll probably fix it right there. I'm not counting cells, I'm counting bytes. Yeah. Okay. I think that fixes it right there. Oh, I forgot to remove that last %V. Go. Okay, this should hopefully jump to the right place. It does not. Or at least it doesn't seem to. Oh, we need to increment the A register. We don't need to, but I want to. And I want to load 5 into the A register in the first place. Boom, we load 5 into the A register. We execute the call instruction. And we are storing attempting to store 81A into the program counter. And that is not the right address. Yeah, we do need that divide by 2. Yeah, okay, let me see. Wait a second. No, we don't. Yes, we do, because it's multiplied. Yes, because the address is multiplied. Okay. Let's change this up a little bit. I'll have to fix it when we come back. Now. So that wasn't the problem. Okay, we get D. It's 13. Basically, we're saying to jump to 26, which is right here, which is correct. So why in the hell isn't it working? Load call. Execute call. There we go. Now we jump there. But we return back to the LDI instruction. No, we don't. So now we execute return. And now we go to the next call instruction. Okay, we've hit a halt instruction. We should have 10 in the A register. And we do. Alright. Let's just make sure the assembler generates the right output. Real quick. OXOD, OX80. Okay. It's correct to me. That'll give you a slightly better idea of what I actually see. My Sublime Text is scaled down smaller than what it is on OBS. But I can see more over to the game window side. The way I have it currently positioned on my desktop. Anyway. We can execute calls. Return seems to work. Jump seems to work. So, it's time to move on to the next stage. Okay, how do I interface with the console? It says offset. Well, that's great and all, but what do I write to it? Let's fix the offset to 0. I guess we don't need to do anything. Let's write a real simple program to try something. Boom. Okay. Wait, why am I doing this? I don't need to do it here. I can just do it here. We don't need to do any jumping or anything like that for this program. We just do LDA 100. The I 100. And then we do STAIO. Okay. Nope. Just writing to IO does not write to the console. Well, do I just write to the offset pin? Like, we can choose a text code page. Using color mode doesn't seem to do anything. Like, how does this thing work? Because I definitely want to rig in a console and a keyboard input. Eventually. Console's important to have now. Okay, what happens if I just write constant 8-bit values to the console? Let's write 128. Nothing seems to happen. Nothing. What other inputs do I have? Don't tell me that this is part of it. Okay, let's hook it to register 0. And then let's hook a counter to it. Count by 1. Okay. We are going to want to loop here. Why am I working on the output? That's dumb. So we'll load what is the ASCII code for A? Not exactly something I memorized. I probably should have it memorized. $97. I knew it was 90 something. Okay. 97 to 122. I can't use constant here, because then assembler is going to go berserk. Not smart enough to know how to handle that. All right, 97. $122. I should do that first. Store it to R0. Then we load 97. Then we do a label. And we do nothing. Let's see. CMP. R0. Jump up equal. Um, we need to make another label. Okay, otherwise, increment A. We want to reset, and we do LDI 97. And then we do JMP loop. The reason I'm using underscore here is because I kind of use that as a this has no meaning kind of value. And it is defined to equal 0, so with the jump instructions, you could put an offset in here if you wanted to. That's defined to work. As might as well, I guess. But it really has no meaning. And we'll never get to that halt instruction because it'll loop constantly. Okay. Run the assembler, or the label translator, I should call it. Boom. Oh, come on. There we go. Now, oh, jump with equals not a thing. It is jump with 0. Yeah. All right. Keep running, damn it. It thinks it's ending. It's not ending. Keep running. Why does it think that's the end? That's not the end of the program, you piece of shit. There we go. It's because it needs padding bytes at the end. Okay, but the important thing is it's not writing anything to the console. I was hoping it would write whatever. Alright, how in the hell does this stupid console block work? Alright. This patch brings the file ROM while the console's added a few days ago. Console's first a couple display components, allows you to print colored characters and 80x24 display. Yeah, that's great. Ow, you piece of shit. Here we go. It must be linked to a memory source. Okay. Updating the linked memory will then update the visuals on the console in non-standard color mode. In standard non-color mode. Each byte in the memory component determines what the corresponding character in the screen will be. So we need a 256 character memory we can write to. Okay. So we just need to map a memory region to the console. That's much simpler than I expected. And then the offset we feed in would be a constant offset to the memory region, I'm guessing. Let me drag this through the middle of the computer, you piece of shit. There we go. Okay, so this gets connected to the RAM component. And then this is where we feed in the RAM offset. And then we modify this program so that before we increment A, we do LDM, oops, LDMA, no, STM, wrote to memory, except I want to do this a little differently. Namely, I want to do it over here so we can actually use labels properly and they get translated correctly. So we want to do STMI. And then we want to increment I each time through the loop. Also, we need to do another jump here. Okay. Now. Just do it that way. Nah. Screw it. Okay. Wait, why am I doing it this way? I don't need to load these into registers at all. Because I can do CMPI 122 and CMPI 255. Okay. And then let's do a little STA R0, LDA I, CMPI 255, and then we do. Actually, I don't need to do that at all. I could just compare to 0. Because if when it rolls back around to 0, or we can just let it roll over. Actually, you know what? That's fine. We'll just let it roll over. Because who cares? We do, however, need to loop here as well as here. Alright, let's rebuild that little program. Oh. Definitely not writing the right values out. Because it's jumping back up here every time. What the hell? Okay. That should have run the LDI. Here, restart. Boot has run. That should have run LDI. That ran CMPI. Which should not have set the 0 flag. That should run STMI, which indeed it did. Increment A. Which indeed it did. Increment I, indeed it did. And then this should jump back to CPMI. I think it... No, it didn't reset the system. Yeah, it did. It ran LDI again. What? Yeah, running LDI every time. So jumping to here is actually jumping to here. So we're jumping to instruction 1. This is instruction 0. This is instruction 1. Then we're multiplying the instruction number by 2 to get the byte number, because every instruction is 2 bytes. And it's somehow putting us here anyway. What the hell? Okay, that ran the boot instruction. That ran LDI. That ran CMPI. That ran the jump instruction but didn't go anywhere. That ran STMI. That should have run increment A, and it did. That ran increment I. Now this should run the jump instruction. Or I'll load the jump instruction, run the jump instruction. Okay, what is it trying to write? Trying to write a 0. What? Okay. Requesting a memory load. It's getting a memory load. The value it's getting is an obvious program counter value. And that is not going anywhere because this is not connected up any longer. What the hell? How did that become disconnected? Alright. Well, that would explain why the computer wasn't working. Oh, I wonder if it accidentally got a component drug on top of it. I think it did when I was moving the console around. Alright, reset, run. Yep, A, B, C, D, E. Okay. Where's the run really fast button? I'm gonna put some padding here in the end so it doesn't think it's reached the end. There used to be a run 10 kilohertz button. That seemingly has gone away. Well, it's slowly filling the console with characters. Why is it stopped? Oh. Damn it. Okay. I see the problem. We can't give this an address that's out of range. Otherwise, it'll think it needs to stop. So we need to actually put a switch on this value and feed it off this line. Which we can't do because stupid reasons. So we're gonna have to do a bit indexer. Which we can't do. But we can do it before the switch. Okay. Now, anytime it's not directly addressing this, it'll give this an address of 0, which should work. I kind of need that run at 10K button. I might need to go do one of the actual levels. It goes up to Y and then it resets. Because we have an off by 1 error. Let's start it out at 96. Now let's increment A before we print it. Not there. There. Okay. Which means we don't need this padding byte anymore either, probably. Because we should never address beyond the end of the addressable code. Actually, it might not like it when we hit the reset point. We'll see. Had an emergency and had to run. Well, hopefully it wasn't too big an emergency. That kind of thing is never fun. At least I've never heard of a fun emergency. Okay. X, Y, Z. Boom, it did exit. Okay, damn it. Continue running, you piece of shit. Alright, so we do need to pad the end of the program. I am going to just go ahead and add that to the assembler real quick. Because it doesn't hurt. Okay. We'll just add 4 bytes of padding, because that'll be should be plenty. All right. And also, let's fix up this program that doesn't have the off by 1 error. Okay. And there's your output assembly. All right. I do believe the time is rapidly upon us to do something actually useful with this computer. Let's just pick a random. I will do this one. Why the hell not? Oh, it's not going to allow us some of the sandbox stuff, is it? Why is... Okay, network, time, keyboard, and file loader are sandbox only. The displays are apparently available anywhere. Inputs and outputs and the level screen are level only. Why don't we get the damn 10K button right here? Okay, let's select our program. And let's go ahead and relabel all this stuff. Last occurrence of label? Yes. Okay. Now we need to fix these. We just do ret instead of popr. The jumps all need dummy instructions added. Call does not, because it's special. Okay. It's actually somewhat important we load these to 1 and 2 because 0 is going to be used for the screen. Okay. That should be everything. Run the assembler. Okay. We'll load the Shin 16 schematic. Okay, these do not exist anymore. These need to be changed to LD high, LD high, and then we do STA, RP, no, DP, and then RP. Okay, there's some other changes we need to worry about. Namely, calling conventions have changed. This calls no function, so we don't need to do anything special. And we only call a single function, scan forward, in here. So we don't actually need to change anything about the calling conventions. But if our functions call the function would have to preserve the return register and restore it before returning. So, make sure this still works. It most definitely does not. Oh. This is definitely not the right code. Okay, let's copy the new preamble. Replace these. Let's run the label translator. Copy that code. Replace this code. That's LD high, not write to output, you piece of shit. Okay, we're definitely loading into memory. As you can see, characters showing up in the console here. Okay, what did it output? I can't even see where the previous instruction was because it sets it back to 0 every time when it actually executes the instruction. Which it has to do because of reasons. But it definitely is hurting my debugging. It should be here that the problem arises. No. STAR0. Okay, where are we writing to the IO? This is loading IO, that's fine, but where are we writing to the IO? STAIO, right here. Alt 0. Okay, what the hell is it doing? Can I not run to a breakpoint anymore? Apparently not. Okay. Definitely not doing the right thing. All right. Let's set a breakpoint after it finishes loading. Okay, LDMI 0. STAR 0. Boom, that did the right thing. Now we call scan forward, which is here. We push K. We push R0. LDI. We jump to the end label, which is there. Or not. We could possibly jump to the continue label. Okay, it's completely off the rails. Who knows what the hell it's actually doing? Yeah, this is going to be particularly hard to visualize because of reasons. So, why is it going off the rails? Are the stacks screwed up? Entirely possible. Let's hook up the registers because they're unhooked. Okay. And then this one goes back to normal registers again. Oops. Damn it. Okay. And these are the general purpose registers at the end. And we just have enough room to fit everything in. Boom. Now, boot has been run. There we run LD high. Actually, this is not right at all. No, it is right. Yeah. Okay. Let me store that RP. You know what? The overflow for the stacks is meaningless now. There's no way to detect a stack overflow this way. You'd have to do it in software. Unless we had software settable overflow limits. Or hard-coded stack bases and stack sizes. Both of which are somewhat reasonable, but I don't know. Okay. Boom. Now, we finished loading the initial values. Now we have LDI 15. Boom. Throw that to the I register. Boom. Why did we have an insanely large number in I anyway? Oh, because you're writing to memory. That doesn't make any sense though. Whatever. Anyway. Current column height, LDMI 0. Boom, that loads a 4, which is correct. We store that in R0. Call the scan forward function. We run push K, which K is 0. We push R0, which R0 is either 0 or 4. I don't remember which one of these is R0. Oh, this would be R5, R4, R3, R2, R1, R0. LDI, STA, LDA to I. Okay. STA to K. The increment K. And jump if negative, which it's not negative, so we shouldn't jump. We do LEMK instead, which gets to 6. And this is the forward scan loop. And it runs right off the end instead of doing its thing. Why does this have 2 comment markers in front of it? Oh, because continue is a label and continue FL is a label. Alright. That's the problem with search and replace. This got the wrong value here, I think. If I change those label names, it should fix it. That's really annoying, though. This is why you do smarter systems than search and replace. But oh well, laziness can only get you so far. We're going to call this one continue scan. Whether that actually makes any sense or not. But wait. That is a good point. Does that make any sense? Oh. No, we're going to call this skip set max. Okay. File that. Look for any obvious goofs of that particular nature. I don't see any. It got to 20-some thousand ticks. That's way more than it takes to run this. So it's never exiting. Why is it never exiting? Here, actually. Okay, there we go. Now, I'll scan forward. And we'll just watch the value of the K register. It is counting down still. 4, 3, 2, 1, 0. And now it's negative. So we jump to the end, or we just fall through to the end. Then we pop R0. We pop K. And we return. And we go back to the load stage. What? Okay. We're back to where we were. Jump negative. Oh, I see. We forgot a thing there. We better fix that in the source code. How'd I miss a jump? Well, pretty easily, probably. But I missed 2 of them, apparently. Okay. Let's look for instructions that start with a J. Have 1 or more word characters, a space, and then do not have an underscore. Actually, yeah, 1 or more space characters. And then have a character that is not an underscore. Unable to find. Okay. If we remove that, we have 8 matches. Okay. That should have fixed that problem then. On the assembler, grab the output. Okay. So we solved that puzzle on the Shin 16. Not particularly revolutionary or anything, but it does mean the Shin 16 mostly works. Whether it completely works is another story, but most of the basic functionality is there. Now the fun begins. Because this program is boring. Nobody cares about this program. Okay. So, what I want to do is translate this in very broad terms. This is a 64-bit fourth that only half works. As in, the basic fourth interpreter works, but then I never actually implemented, and mostly any of the words you'd actually need to make it actually do things. You can, add two numbers together and really basic stuff like that. Define new words, but you really can't do much with it. Well, let's make a 16-bit fourth. And then let's see if we can solve this puzzle with it. Good luck getting that done tonight, though. Well, first things first, I need a way to define constants in my assembler or I'm going to go insane. So, let's go ahead and insert some logic in here to add constants to the assembler. We kind of already can for labels. Constants are going to have to be 8-bit. Because most load immediate stuff can only load 8 bits. This is why I should have wrote a real assembler. Then I could have things like macros that would automatically load 16-bit values, stuff like that. Part of me wants to go write assembler now instead. The problem is, if I want to write assembler, I don't want to do it here. Because I'm not set up for proper development here. I can do crude development, but it's going to drive me nuts. I don't have any of my good tooling set up over here. I did import some of my Sublime settings properly from Linux. But there's still things missing. And I did set up a new Go compiler and stuff like that. Oh, yeah, no, let's not do that. Do constants. All I need to do is if string has prefix const, ignore that line. And then we can define 8-bit constants the same exact way the Shin would. Or, the in-game assembler would. Alright. So first things first. I don't know if I actually want my stacks to be at these base addresses. Yes, I kind of do. Also, I don't know where exactly I want to put... I kind of want to use the first 256 cells as global variables and stuff like that. Let's load high 2, load high 3 for the stacks. And from 256 forward will be the console buffer. Okay. Okay. Oops. And then 512 to 767. B stack. And 768 to 1023 are the R stack. Now, 1024 and forward is going to be the main memory, I think. Or the dictionary, in this case. Okay, so everything in the early memory is going to be globals. So, this is obviously written for byte addressable systems. Our system is not byte addressable. Our system is cell addressable, where the cell is 16 bits, or word addressable. Unfortunately, I wish it was byte addressable, but I wasn't able to get that working with the way the RAM works. I probably could have gotten it working in the end if I'd banged my head against it long enough, but I decided it wasn't worth it, and so we dropped byte addressability, which is going to come back and bite us a little bit when we have to do string processing. But thankfully, the kind of string processing we need to do is pretty simple, so hopefully we don't have to worry about that too much. Now, we're not too worried about the system size. Word names in cells. So in this case, I allowed 32 characters for word names. It's probably a little excessive. I think we're going to allow I set word name max to 8. That'll be 16 1-byte characters. That should be plenty. And that'll allow us a byte for the word name length and a byte for the flags. And we don't even need that much, because we could store the word length and the word name length in half of a byte. 16 characters, you know. But if we do 15 characters, okay. Four bits is more flags than we need. That should be good enough. Okay. In the original Forth, the system memory is just defined as a byte array, a large one. Originally, I defined the R stack as 128 cells and the D stack as 512 cells. I don't think we need to define the stack sizes here, but if we need to, we'll come back and do that. Word buffer size. This was in bytes. So the word buffer is used to read text from the input. And so having this be a reasonable size is somewhat important because it has to hold the entirety of a single token. So it needs to be at least 16 characters long, probably more, to hold the name of a word. And it should be a little longer than that to make sure it can hold a maximum size constant, which 16-bit maximum size is like not that long. So we can define this as being a little bit larger than the word name max. Okay, word buffer length. We'll just go ahead and define it as 32 bytes. I might want to change this to cells later. Yeah, we'll just change it to cells for now. If it needs to be bytes later, we can figure that out. Okay, line buffer size. This is the length of an entire line of entered text, from the beginning of the line to the end of the end character. Technically, we don't need a line buffer. I don't think. If we do completely unbuffered I/O, which we might do because we don't have support interrupts on this system. So there's no real way to fill a buffer off to the side. If we're reading input, we have to be reading input actively. So I don't think we're going to bother with the line buffer. Okay, globals. This is how many cells to reserve for global variables. I used 4, but I'm going to need more than that. Because we can't have global variables outside of the stack. Not outside the stack, but outside of the system memory like we did in here. Because, like, these error flag, the error flag and exit flag, those are going to have to be kept inside the system memory, because there is no other memory. So, actually, let's just put a comment at the top of this file to explain what it is. All right. I don't think we actually need to define a constant for this, but we'll set it at like 6 for now. It's going to have to be more than that later. Okay. This is why I want to have all my global variables in the first 256 bytes. Because that way I can refer to them with constants. So, we will do error flag is 0. Exit. The exit flag is 1. These are cell numbers. Okay. I need to, yeah. Let's see. Stop looking at that, that's not useful. IP. Keeping in mind that this is the 4th instruction pointer. Does this need to be separate from the normal instruction pointer? Maybe? Almost certainly. No, because it's a pointer into the dictionary. And we're going to be calling IP a lot. I don't think I need a separate instruction pointer. We will see. Okay. Last word. Dictionary end. Base. And if we are compiling or not. It would help if I had spelled that anywhere even approximating correctly. There we go. Line buffer stuff, which we're not going to be using a line buffer, I've decided. Word buffer stuff, which is important. This is going to be a nightmare dealing with string processing in here. Okay. Wait. How does the STM instruction work nowadays? Store value in A to memory. Parameter is an address from a register. Okay. We'll do... LDI. Base. STA. R0. STM. R0. Because the high bits are zeros for this address. We don't need to use LD high and then do STA. I was loading a very funny dread. We don't need to use... Yeah. I want as many constant addresses as possible to be in the low 256 bits. I don't need to use 3 instructions to load an address instead of 2. Why am I storing it to R0? Oh, because A is holding the value. That's right. 4 instructions just to store a single value to memory. Okay. How much we can do about that? We do need to store 10 into base. Because base is used for number parsing later. And the cool thing about base is that you can just change that number to anything you want and parse numbers as whatever base you want. It's kind of weird. Okay. Compiling needs to be left to 0. Dict end can be left to 0 for now. Last word can be left to 0 for now. I mean, no. No, they can't be. Okay. Want to store the start of the dictionary. Oh, I need to have the actual start of the dictionary defined as well. There. I'm actually going to load multiple addresses and store the same value to all of them, I think. Wait, I can just use inc r0. There. Okay. That's a little bit. I kind of want to do this here. Okay. Base 10 is the default number parsing. And then we can't really define a start address for the console buffer unless we put it in a dedicated register, which is entirely possible. Like, the machine doesn't need a dedicated register, but we could in our software define that this register is the beginning of. And I should do the same thing for the stacks. Using I or K would make it very easy. To write to the console. Oops. But I don't want to do that. What registers do I have available? Okay, A is obviously out. I and K I want to save for other things. Flags is obviously out. PC is obviously out. EP and RP are very definitely out. Return address is out. Frame pointer. I would like to have that available because it does have some interesting uses. Yeah, it's mostly for dealing with stacks. We could do some fun stuff with the D-stack by using the frame pointer, so we want that available. Level IO is obviously out, we need that. So that only leaves general purpose register. We could use R5. We need to load high, 1. STA. Well, we don't actually need to do anything special about this. because it's just load high 1. Get access to the console buffer. The first address in it. The same way with the base of the D stack and the base of the R stack. They're just load high 2 and load high 3. And load high 4 is the start of the dictionary. Matter of fact, if we just go ahead and check here. Okay. We want 256 to be the beginning of this. Yeah, the first 255 are globals. The second 255 are this screen. The next 255 are the R stack. The next 255 are the D stack. I'm tempted to add more than one screen, so I can view the stacks. It'd be kind of meaningless. But you'd at least be able to see what cells are used and such like. I don't know. Probably not. Alright. Oh, so I think we about have our basic memory layout defined. Now, we probably should do more or less just write it from top to bottom, the way it's written. So here we have functions for writing a character to the console, a string to the console, and a number to the console using the current base. Apparently I wasn't feeling very charitable when I wrote this. I'm not a big fan of C++. But anyway. And this was written to use a null terminated string because I pretty much had to. I wanted to be able to write string constants out. And unless I wanted to count characters and... I mean, I guess I could select every string and count how many characters it contains and then figure out how many of those are escape characters and... Yeah, no fun. It's easier just to have null terminated when you're dealing with C. However, for this we are not doing null terminated strings because null terminated strings are a blight upon this earth and no one should ever touch them. So, let's insert a halt. The actual start code will go right here. And below this point, we'll go functions of various kinds. In this case, output functions. So we have write C for write character. Write S for write string. And write D for, I guess, write decimal, but basically write number. I'm going to document them. Oh, I'm going to have to deal with scrolling the console and stuff like that, aren't I? Yes, yes I am. Well, there are a couple ways I can handle this. I can move the dictionary up one batch and then define a scroll position for the console and have a double-sized buffer for the console. And you just write to that buffer, starting from the top, going to the bottom, and then starting over again, and then you just have a window that moves with it. So by the time you reach the bottom of the buffer, you have a whole new empty console window above you to start over. That seems... like a bad idea. However, scrolling is going to be incredibly unperformant to do any other way. It's not going to be any more performant unless... How am I going to handle scrolling? Oh. Okay. We can write, every time we write text, we can write it to the console twice. Offset from each other by 256 bytes. And we can, every time we get a new line, we can move the console offset down one line. Forward 24 cells. 24 characters, which would be 12 cells. Actually, I don't know if this console is going to work properly. I just realized it is writing one character per cell. I needed to write one character per byte. Which means we are going to have a whole separate RAM bank for the console, and we're going to have to build console hardware that talks to the RAM, and then we write to the console, and the console handles its own scrolling, which is kind of what I wanted to do in the first place. So we need to have a smart console with its own hardware. Let's go ahead and grab a RAM chip. Just a simple fast RAM will do. Okay. 256 bytes, 8-bit data width. Connected to the RAM there. Alright, now we're going to have an instruction that writes a byte to the console. It's time for group 3, I think. Because group 3 is going to be I/O. And then to handle scrolling, this needs to be 512 bytes. And then we'll just scooch the offset down until the offset triggers a certain value, and then it'll go back to 0. Scrolling the console buffer. So we're going to need a couple values here. We're going to need an 8-bit register. Store that. We're going to need an 8-bit register. We don't care about load. We only write. Okay. This, on the other hand, needs to be constantly energized. For load. Okay. Now, let's just write the scrolling code first. Before we actually start figuring out how we're gonna... Like, writing to this is gonna be pretty easy. Oops. We're just gonna have an 8-bit input. With a enable line. And we'll just say right in. Now, bit constant. We set that to 10. Okay, when this line goes high, we need to scroll. So we need to add 24. What exactly all does manual say about the console? Okay, we're not doing color console yet. Okay. 80 by 24, so it's 80 lines, or 80 text, 80 characters across, 24 tall. So we want to have an adder here. And whenever it's time to scroll, we want to add 80 to it. Okay. Now, we also want to trigger okay, every time this ticks, the load needs to be constantly energized. The load can be constantly energized. I don't think we can connect like that. Oh, we can maybe. Okay. So every time we request another character be stored, it increments this counter by 1. Writes that value. Okay. We'll just go ahead and fix that on for now. And we will write a whole bunch of A's. Okay, it's not increment. Oh, because we're not energizing the door. Or the load, I mean. Okay. Now, we need to get the current counter value modulo 80. And I think we're better off not doing this mess. I mean, we need some of this mess. But every time the counter value is modulo 80. Okay. This should not be triggering this counter. Or maybe it should be. But it also should be triggering... Okay, this is a complicated pain in the ass. Okay, there's several conditions we need to handle. We need to handle going to a new line. We need to keep track of what line we are on. So we need to do address modulo 80. And if the address gets too big, then we need to increment. So this is wrong. This is the scroll counter. Hello? There. Okay, this is the scroll counter. This should only trigger when this is triggered, the screen will scroll one line. We don't want to scroll every time we hit and enter a new line or anything like that. Otherwise, we would never show more than one line of text. We want to scroll, we get to the bottom. So when the address goes higher than 256, then we want to scroll. I wonder if I should use dual load RAM and to save two values. Yes, I should. I think. Because we need to store one value here and then one value offset by 256. So this character needs to be fed into there. Oh, we can only save one value at a time. That's right. That's not useful to me. All right. All right. Be that way then. Yeah, we don't need to do that. We can still keep going properly, I think. No. Yes. No. No. We got to use the clock here. Because we do have to store two values. If we don't store... Actually, I wonder what happens. Okay. Let's set this to 256 bytes. Now, what happens if we set the offset? Let's just move this out of the way for a bit. To, say, 128. We just start storing A's. Okay, obviously nothing happens for the first 128 bytes. Which is not what I wanted to see. I was hoping it would start filling from the middle of the screen. But this means it doesn't wrap around. If it wrapped around, our problem would be solved. We could just go for it. $66 mining now? No? Getting up there. What is it you need to get into the mining guild again? It can't be much more than that. Oh wait, you're in the mining guild already, that's right. Now. The mining gloves are super nice outside of Motherlode. Completely useless inside of my Motherlode, but outside's very nice. I was mining a little bit of amethyst for cash last night. And there's a bunch of times where I got 2 or sometimes even 3 chunks out of one wall, which greatly decreased the amount of attention I had to pay to it. But if you're in Motherlode, there's no purpose to getting the mining gloves. And I would recommend doing Motherlode first, honestly. Unless you're one of those nut jobs that goes all the way to 99 with mining iron. Which technically is really fast, but why would you do that to yourself? Okay, so this RAM must be 512. And we need to have an alternating clock signal. So we can store once at the address, once offset from the address. Let's just go ahead and grab clock right out of the middle there. Bring it over here. This will hopefully be temporary. Really, why am I grabbing clock from there? We'll just have our own clock for now. We don't care about the main system as a whole at this point. Why am I even implementing this? Go to the component factory. New schematic. ATY. It won't let me place a screen. Screw you. Of course. Okay. In that case, switch schematic. We'll just do a whole new computer. There we go. This should at least run a little better, hopefully. Alright, so we've got a clock. Which will hopefully cycle for us. Now, grab a keyboard. And we will attach that to the clock. And we'll latch that into an 8-bit register. Okay. Wait. It gives me 53 for the enter key. kind of bizarro. Okay, it's definitely not translating it to ASCII. That's nice. Please tell me it at least outputs. No. Okay. Yeah. Oh, character mode. There we go. There we go. Wait, why is it not putting 5 for the enter key? That should be 10. Please don't tell me it's outputting like a carriage return or something. No, it's 13. Why in the hell would it output 5 for the enter key? That's insane. What is the ASCII code 5? Five is ENQ. What the hell? That makes 0 sense. One is negative acknowledge. That's what plays and press shift. Tab is 2, which is very much not correct. That should be the tab key. 2 is start of text. Which, why would you do that? Backspace is end of transmission instead of delete or backspace. Okay. That is a special kind of insanity. Okay. Apparently all the non-alphanumeric keys just display whatever in the hell weird value they want to display. The delete key gives backspace. The backspace key gives end of transmission. Keyboards produce scan codes, and then, yeah, I know that. But I have it in character mode. If I had it off character mode, like, see, I would expect this to be a character mode by default just because they don't bother to explain this component, and so I would kind of assume it would automatically be character mode. I mean, this is obviously giving scan codes, which annoys me. But if I turn on character mode, then space does exactly what I would expect, 32, which is space. Backspace, on the other hand, gives 4, which is completely nonsensical. Now I turn off character mode. What's backspace give me? 26. So it's not outputting the scan code when it's in character mode for non-alphanumeric keys. It's just doing whatever insane whack job stuff it wants to do. Because delete is 8, which is backspace. Pressing the delete key gets you backspace. Enter is not 10 for new line, and it's not 13 for carriage return. It makes no sense. But at least the alphanumeric keys are sort of correct. Also, what is this event waiting line for? It does nothing. Unless... Okay, what happens if I hold this high? Nope. So we can't even get interrupts out of this thing, even if we wanted them. Interesting. So we either have scan codes, for which I would need to make a big translation table, or we have slightly more insane scan codes, where at least I don't have to translate the letters. Okay. I guess I just completely ignore ASCII and go with 4 for backspace and enter for 5 for enter. And 21 for shift. Yeah, it looks like they just assigned all the non-alphanumeric keys, whatever weird thing they wanted. What's escape? 1? Okay. No, there is an actual escape character in ASCII. It is... 27. Hello, Treebeard. I have just discovered that the keyboard input, when set to character mode, does not actually output ASCII. It pretends to, but it doesn't actually do it. Alright, anyway. Oh, I need to set this high, of course. Would help my energized store. There we go. So wait, why don't I just tie those two together like that? Then again, If this means what I think it means, then what I really want is to only energize store when the key is up. Go ahead and try this. Okay, we can get characters out. All right. Now, I need to clock this on 2 cycles. Go ahead and move this little bit out of the way. We'll check for equality against 5, because apparently that's the code for enter. This will be a new line indicator. Go. Okay. This monstrosity handles counting. We need a 16-bit shift, actually. Okay. Now, eight-bit constant, shift it by 8. And then we need a 16-bit mux. Okay. And this gets tied to the clock. I think. Yeah. Yeah, we just tie that direct into the clock and we should be good. Do that so we can easily make room for this to go up through. Okay. First clock tick. Oh, we're not actually energizing the store line. The store line needs to be energized by this. Which needs to be on at all times. For now. Did I not set this to 512? I did not. Okay. I want a delay line. Wait, why did I shift it? We don't want to shift it 7. And also we need a delay line. There. Okay. And then we want a diode and a delay line. But this stays energized 2 ticks. We need a 1-bit switch. Boom. And we need an 8-bit switch. There we go. We need to copy this mess here. But with an 8-bit delay line. And an 8-bit mux. And that connects to the clock. Could have actually done that way. The only important thing about this is that it connects one of the lines now and then one of the lines 1 tick later. It doesn't matter which. This might not work because of multiplexer fun and games, but indeed it doesn't. Boom. And then next tick. Boom. Okay. They did 41 out of 158 quests. Not sure how far along I am. Probably not that far though. I don't know actually. I've got a bunch of fossils from training Melee on Fossil Island. and magic on Fossil Island. I should probably clean. If you haven't already, I strongly suggest you clean stuff at the dig site. At the dig site? At the museum? I don't remember. I think maybe the museum, actually. No, it was the dig site. Damn, I don't remember. Anyway, I suggest you clean finds until you get the enchanted necklace that you can use to learn how to make more teleport necklaces for the dig site. Because being able to teleport quickly to Fossil Island is pretty useful. You got it? Cool. I overlooked it the first time around somehow. And then I had to come back and get it later. Yeah. Building the bank chest on Fossil Island was also super useful. I built the bank chest and everything else that's there. I haven't done like any construction training at all. I just got it all through quests, but I'm in like low 30s or something. Doesn't take much construction training to get up high enough to build the stuff there. Okay. We're holding the store line high. The address line. It's not incrementing. Except it is incrementing. Like right now, move this out a little bit so you can read these lines. Multiplexer's backwards, that's what the problem is. See if I can get a NOT gate in there. Doing a shift left. Okay. If I take a 16-bit shift left and feed in 7 and a 1. I should get 128, yes. That's what I thought. I feed in an 8 and a 1. Then I get it shifted to the high byte. Okay. If I put in a 255, then I get pretty much exactly what I would expect. Okay, that is not what I want for RAM though, actually. Upon second thought. I just want to add 256 to it. I'm being a derp. Oh, 255. Okay. I got to move some of this stuff back. Boom, like that. We need to add more than 255 to it. I need to add 256 to it. All right. Boom. We could use a 16-bit constant, but this is easier. Okay. Let's change this to 256. Let's change this to a 16-bit constant. 16-bit constant. Not delay line. There we go, constant. Boom. Okay. Did I forget to hook this up again? Yes, I did. Boom. First store cycle. Second store cycle. Third store cycle. When the clock is low, it stores to the first half of the buffer. When the clock is high, it stores to the second half of the buffer. And that's currently displaying the second half of the buffer. The blast furnace runs, you go to the blast furnace world. Yes, because the way the blast furnace works is fundamentally different on the blast furnace worlds. The way the blast furnace works normally is that you have to get a bunch of people together, and different people run different jobs on the blast furnace to make it operate. You might find a group of friends large enough and willing to do it. Good luck. It's a fiddly, annoying minigame from what I understand. On the blast furnace worlds, you pay X amount of gold per hour, and the blast furnace is run automatically by NPCs. And all you have to do is dump your ore. You need to pay for access to the blast furnace if you're under a certain amount of smithing, I think. I don't have to anymore. But nothing will stop you from having to pay the 70k per hour You have it run by NPCs. And you really, really want a coal bag for it. And you also really want to spend the money for stamina potions. Because you want to run constantly. And if you can get it, you want a graceful outfit. But yeah, doing Blast Furnace the normal way, I don't think anybody does it. And I'm not sure why they thought it was a good idea to add a multiplayer minigame for smelting. Yeah, I don't have full graceful myself, but I should. I need to do more rooftop courses. It's just they're just active enough that you can't just sit back and do nothing like you can with some kinds of mining. And they're just inactive enough that they're boring. Oh well. Okay, so we finally got it, so it's storing stuff twice in RAM. Hopefully this will allow us to do scrolling. So what we need to watch now is when this address gets to be over 255, or when it rolls over. When this address rolls over, we need to scroll the buffer one line and subtract 80 from this address. And the scroll buffer circuit, when it goes to add 80 and comes out as 512, that also needs to scroll over. Or rather, when this rolls over to 0. So when this overflow lights up, we need to do not do anything. I just realized that we don't need that after all. I don't think. Damn it. This is a lot more than 256 characters, isn't it? This is 1024 characters. I think. What is 80 by 24 again? I just realized, yeah, I think it's a full screen. Um, 1200, okay. That's even worse. So we need 2400 bytes of RAM. Okay. 2400 bytes of 8-bit RAM. This needs to be all changed to 16-bit. Definitely not going to be able to count on rollover to help us out here. Or fairy flags or anything handy like that. Not sure why I was thinking 256 for this, because it's very obviously not. It's 80 by 24. There's no way. Okay. Hopefully we can clean this mess up a little bit, though. So, let's design a better system for this. Okay. We need a bunch of devices that output for 2 ticks. And change every clock cycle. So they're just gonna have to be like this. Once per clock cycle, this will be fed. And then once per clock cycle, it'll tick off. So we need one of these for the value. We need the smaller 8-bit version for the store circuitry. And we need a completely different (16-bit) one for the what do I call it? Okay. Move this back one little bit. And run the multiplexer down. Like so. And then you get moved back one little bit. Make this a nice straight line. Because I like the way that looks. And this goes into there. No. Okay. So this thing has 2 lines in. It has an activate line, and it has a value line. Activate and value, oh yeah, and 3 lines in, and clock. Activate and value need to be on only every other clock tick. This needs to be a 16-bit switch. Okay. Unfortunate. Of course, I have to move it a little bit. Okay. Value, activate, clock. The clock can be completely internal. Matter of fact, I kind of want it to be completely internal. Okay, this is the address, which is internal. This is exposed to the outside world. Why did I hook the clock to the activate line? I don't know. Why do I do anything? Okay, now it's hooked to the clock line. These two can go to the outside world. They are where we feed in our values. Clock will probably feed in from the outside as well, so we can synchronize it with the rest of the computer, but from the outside, we're not actually making a chip out of this. We're just going to copy this into place when we're done. Okay, those are connected. Now, so this part handles double storing the RAM. Now, every time we do a store, this line will go high. Why is this connected to the clock? That is completely inappropriate to connect to the clock. This, on the other hand, must be connected to the clock. There, that is correct. Okay. So this tick, we are going to store this can be an 8-bit value. Matter of fact, it should be an 8-bit value. This isn't an address, it's a character. Okay. Now, we're a little closer to handling scrolling. We need to this actually make a huge problem, I just realized. When we get to the end of the buffer, and we need to move down a line. When we move down a line, we need to blank the new line. We can't blank the new line. Not without stopping the computer clock, advancing 80 ticks, wiping out a line each time, and then restarting the clock and going ahead. Because we can only access one memory cell per tick. We could detect idle ticks and blank RAM behind us out of the visible area, or maybe I should say ahead of us, when we're not active. However, that is not a reasonable thing to do, because if the user types fast enough for long enough, they're going to start seeing garbage. And I have a feeling it's going to be pretty limited on how fast you can type anyway. Particularly because we have no kind of interrupts or anything that can handle this. It's going to take multiple cycles to store every character whenever we're waiting for input. Because you have to read the character, you have to write the character to the right part of RAM, or in this case, just write the character to the output. Yeah. Because we can delete a whole 1,200 characters ahead. Maybe that's just what we're going to have to do. Blank RAM ahead of during down cycles. Basically, whenever this line is low, or rather, whenever this line is low, just blank RAM. Up to 1,200 spaces ahead of the current address. I really don't like that approach. It's not like there's any way to shift. If we could shift everything in RAM one space every time we type, or shift everything in RAM 80 spaces at a time. If I didn't have to use RAM for this, is the actual thing. Because you kind of would want dedicated memory. Where the memory has dedicated functions for moving a line up, moving a line down, writing a whole line out in one go. Because Well, there's a reason old terminals were designed the way they were, and they didn't necessarily just use... Yeah. We could... No, we can't increase the... I was about to say we could increase the bit width to allow us to write more at a time, but no, we can't, because then it's gonna be weird. Oh, I think. So if I could like use 64-bit registers to store each line, use a couple of registers, and then just apply logic that when you hit this certain line high, it just shifts everything up one. Or even 8-bit registers. That'd be a huge field of registers. A lot of tedious wiring. But it would give you fast hardware scrolling. Which is what I'm trying to do here. I want hardware scroll. I don't want to have to mess around with tons of software. Because if I have tons of software console handling code, I am going to have to deal with it being incredibly slow. Because this computer is not fast. I suppose if I ran it in fast forward, it might work. I can't believe I didn't foresee the problem of having to blank lines. Yeah, because it's not something we can do in a single cycle no matter what. How badly do I want hardware scrolling on a console? Software scrolling is relatively straightforward. Let me check something real quick. Okay. I think that what I'm going to do is what kind of displays do we have? We have a 6x8 dot matrix. We have the console. We have a multi-layer sprite display. And a 7-segment display. Which is utterly unsuitable. You can display characters on a 7-segment display. But making any kind of console with a 7-segment display would be entirely possible. We would need well over 1,000 of them, though, to even make a simple 4th screen editor. A 6x8 dot matrix, that's enough to make a character. But once again, we would need over 1,000 of them. Really, the 80x24 character console is all we really have an option. I would kind of actually like to do a block editor, a hardware block editor. No. Okay, you know what? Let's leave this alone the way it is right now. And let's go back to the Shin 16. Where did I move that display to? I deleted it, that's what I did. Okay. So let's go ahead and let's hook a display up. Do the system RAM. And then we will set a hard-coded memory page. Okay. So let's move the stacks down. And let's move the screen up. Okay. Let's give 4 blocks. Let's see. 2 blocks is 512. 4 blocks is 1024. That's actually not enough. We would need 5 blocks of memory for the screen to get 1200 characters. Yeah. No. Oh, oops. It would help if I wasn't in hexadecimal mode when I was trying to do that. Yeah, that would get us 1280, so we'd have 1 extra line. Okay, we'd have to do 5. We have to do 5 whole blocks. Okay. Okay. The dictionary is going to start at 2048. So the 0 block is globals, 1 block is dstack, 2 block is rstack, 3 block up is the console buffer. The 3 block, the 4 block, the 5 block, the 6 block, and the 7 block. And the 8th block is the dictionary. The 8th block to the end of memory. Okay. Now, yeah. And we're just gonna have to do scrolling somehow. It's going to be slow. It's going to be a bit shit. But it's gonna be done in software. Because I can't be bothered mess around with it. So starting at address 768. I'm debating whether or not I want the blank line to be at the beginning or at the end. Because that one blank line is going to be our scrollback buffer. Such as it is. We're not going to probably use it for that. But I wonder if it would be easier to implement our scrolling if we copy the first line instead of just copying the second line into the... No, it would make it slower. I think we're just going to do from 768 forward because that'll be a little easier. So, we need to go set this constant to 768. And then back to Sublime. Actually, wait. Yes, that is good. Yes, that is block 3 forward. Okay, good. So, right character. We need to have routines for scrolling the buffer. Let's do that now. Scroll console. I only care about scrolling the console down, or scrolling it up, or whatever. I don't care about... There will be no scroll command. It'll just be when you type too much text, the top stuff will scroll off the top. There will be no ability to scroll back and look at what was there previously. Nothing like that. We're not being that complicated here. So, we'll push the A register right away. Pop the A register at the end. That way we don't need to worry about who's doing what with the A register when we get in here. This will scroll the console by one line. So, what we want to do at this point is we want to copy every character in the second line to the first line. And then from the third line to the second line. And so on. And I think the way to do that for us is going to be to load 0 Now we need to push I and K. Push I. Push K. Pop K. Pop I. Okay. We want to load 0 into I. And we want to load 80 into K. And then we need to copy K to I. K to I, K to I, K to I. All the way through. Until K is... Actually, this would be perfect. If we had the blank line at the end, we can just copy the blank line up one. We don't have to do anything special to blank out the last line. As long as we never write anything to that last blank line, we can just use it as a blank line. That is perfect optimization. I wonder if that's actually why they made consoles 24 line instead of 25 line. That seems like the kind of weird thing that people would have done back then. It'd make perfect sense. Okay. But anyway, we need a loop. So we can't have a label inside of another label or else it'll get mangled. So we'll do SC copy loop. And then we do at the end CMP. We can't do CMP I, notably. You compare K to A. And if they are 0, wait, if they are not 0, we jump to copy loop. And then we need to LD high. Let's see. The last block is 7. So with the LD high 7. LDI 255. This should get the end of the 7th block, which is not correct. We want 780 in hex. So 0780. Block 7. Character 80. Or actually that would be character 128. Okay, so we compare K to this. If K has reached the end of its rope, actually, let me think for a second here. We actually want 1280. Not 1200. because yeah, we want to stop at the beginning of block 8. We don't need LDI at all. We just need LD high. Actually, we do need this to zero out the low bytes. Okay. Now, we compare K to A. If they're equal, then we break out and exit. If they're not equal, then we haven't reached the end of block 7 yet, and we keep copying. And I think we actually want to use I here, because we're copying from K. No, this is right. We're copying from K to I, and K starts farther ahead. Yeah. All right. So now we just need to carry out the copy part, which we do by doing LDMK 0 and LDMI. No. STMI. It is the right one, right? Yes, STMI. Okay. So we load memory from indirect through K, and then we store memory indirect through I. In other words, load from K, store to I. Then we increment I and K. We check to see if K is at the end. Fail if it is. Otherwise, continue. There are pushes and pops. We don't call any functions in here, so we don't have to store the return register. All right. One console scrolling function completed. Okay. Now, we need some global variables to deal with the console. We need to keep track of what our index is into the console page. Well, we don't care about the console page. We're going to always write to the second to bottom line, or the actual bottom line of the console. We're going to always write to that bottom line, and every time we fill that line, we will call the scroll function. Once we fill the line, we call scroll. Once we fill the line, we call scroll every single time. And write C is going to take care of all of that. But we do need... Let's delete this global count thing. That's bullshit. We're not using it for anything anyway. We do need a... variable for where in the console we're talking about. Console line width is defined to be 80. And then we do console line index is global 7. Okay. Now, first things first. We need to write the character to the current console line index. So we push the I register. Because if we're going to be doing memory access, we might as well just use I. Six more nuggets. Well, it doesn't take long to get those last couple. Nuggets come in pretty quick in my experience. Although it may feel like a lot longer when you only have a few left. Alright, so we push the I register. And we pop it at the end, of course. Then we do LDMI. Okay, we need to load into the I register a calculated value. Namely, we want the base address of the current line, which I am going to have to calculate right now. We need a two-part constant for this because, of course, we do. We want to do, let's see, calculator, help me out here quickly. We're on decimal mode. Okay, 7, whoa, clear. Okay, 80 times 24 is 1200. Let's just do 1200 minus 80 equals 1120 plus 768 equals 0760. Okay, this should be the first character of the last line of the console. Get better odds when you wear the Prospector set? Possible. I don't remember if that is one of the benefits or not. In which case, that would slow it down a little bit, wouldn't it? Oh, let's see. We want LD high. And LDI, let's just load low first because, yeah, why not? Okay, and then we do STAI. Now, the single character we want to write should be in the A register. So we need to not clobber the A register. Well, guess what we just got finished doing? Clobbering the A register. We don't have to preserve the A register through the function call, but we do need to store it off to the side somewhere. And to store it off to the side somewhere, I am going to push R0. So before we start clobbering, I will STA R0. Okay. And then after we STAI, we LDA R0, STMI, you store that character to memory. Okay. Now, we have successfully stored a single character to the console. But if we don't change anything, we will continually overwrite that character. Also, we loaded the base address of the console. That's not actually what we need. We need to have that value okay. We do LDI, console line index, LDM A. I think this will work. Load a value from memory into A, parameter as address from register. Yeah, we can use the A register as a parameter, I'm sure. So this will load from memory, the console line index, and then we just do add I, and this will take the previous base address of the console line and add it to the console line index. And then we do STA I to save it back out. To the I register. And then we do LDA R0 STMI. And that'll save it to the right index on that line. Now, after we've saved the character, we now need to increment the console line index. So, we do LDI console line index again, LDMA. And this will get the console line index in A. And then we do add I 1, or we could do inc A, which is easier. And this will increment A by 1. And then we do CMPI 80. And if it's not 0, we go to and a WC, I guess. Yeah, it's gonna be a problem not having labels, because labels are global. It's gonna quickly become a problem to not reuse labels by accident. But hopefully it'll be okay. We'll see. Anyway, jump not 0 underscore and WC. Okay. If it is 0, then we need to scroll the console. And also scrolling the console should reset the console line index. Where's the console scroll function? Okay, so at the end of the console scroll function, we LDI, console line index, STM. I can easily clobber the I register because we're about to restore it. Let's do LDI 0 STA I STMI underscore, sure, why not? We could just do STM space I as well, but no, that's wrong. We need to LDI STAI LDI 0 because yeah, and STM I. Fine, those will work. Alright. This will reset the console line index back to 0 after we scroll, which should be correct. Anyway. At this point, we need to push RTN because we're going to do another function call. And then we just do call scroll console. Okay. Additionally, we have some special cases to handle. Say the user types a new line. In that case, when we receive a new line character, which is a 10, I don't care what their little input thingy has to say, then we will roll the console. And yeah. So to do that, we don't actually want to write the character out. Matter of fact, we want to do a check here at the very top. CMPI 10, and then if jump 0, end with scroll. We don't actually want to write the 10 out, we just want to scroll. And we don't actually need to restore any of these registers. We don't actually need to push any of these registers either. Oops. There we go. So if we get a new line character, we do the thing. Okay. Additionally, if we receive a backspace character, we should handle that as well. That's slightly more complicated. And actually, this is wrong now. Okay. Oh, what am I going to call this? Okay. Grab that block, paste it. If backspace, delete one character. Now, backspace. It depends on how complicated I want to be. I think I'm going to allow only one. I kind of would need to allow unscrolling if I wanted to do. I think I'm only going to allow you to. You know what? I don't want you to be able to scroll the console when you type. If you type something longer than 80 characters, screw you. Rethink your code, please. Because that's going to make everything simpler if I don't allow that. So we're going to have to do... some extra logic here. We don't want to call scroll console. Instead, we want to LDI console line index, CMPI 0. As long as it's greater than 0, which basically if it's not 0, so jump not 0, we'll just go straight to not backspace, even though let's just call this end backspace. And call that end new line. Okay. And we return from that when we're done. Same with this, return from this when we're done. Okay. Over this. We do CMPI 8. Jump not 0. Okay. We load the console line index. We compare it to 0. If it's not 0, if it is 0, we just fail. No? Okay. If it is 0, that means we've already backspaced everything on this line. We can't backspace anymore. Stop it. Get some help. And so we bail. Why do I have backspace handling? I don't want backspace handling in here. That belongs at a higher level. Except I do want backspace handling here. Yes, I do. Because we do need a way to delete characters from a line. Yeah. Because at a higher level, when we actually write the interactive console code, we will have to filter backspaces out to prevent people from backspacing the prompt. But we should still allow them to delete the line. So we do need to have a way to say, get rid of a current character. Okay, so if we're at 0, you can't overwrite 0. Just get out of here. If it's not 0, then that means we can de-increment A, because we still have the console line index in A. And then we do no, we don't have the console line index in A. Yes, we do. And that's a bad thing. Alright, we need to push A. No, we don't need to push A because we know what A is. We know it's a backspace. Okay, so we can clobber A all we want. I'm being a doof. We know A is backspace. Except it isn't anymore because we loaded something over top of it. Name of the address of the console line index. And then the actual value. There we go. I almost forgot to actually do that. Okay, then we compare it to immediate. 0. If it is 0, if it is not 0, then we de-increment A. And we're going to need to store that off to the side somewhere. The proper way to do this is to preserve a register and store it there. However, if I'm pushing something to the stack anyway, I'm just going to push A. And then we're going to push I as well. Then we do LDI, console line index. Get our address queued up. STAI. And then we do STM I. Oops, no wait. We do pop A. STM to I. And then we do pop I after that. And this de-increments the console line index. And we're done. We return. Okay. Now, the only way to scroll the console is to write a new line. However, you can write 80 characters and then a new line, because we don't check to see how long the text is, we just go. Yeah. Finally full set. Now you just need to grind out the Stardust required to make it golden. That is purely a worthless activity, but it looks cool. Although you should probably grind out the Stardust to get the ring. That doesn't take like an hour, maybe. Maybe 2. The ring gives you an invisible +4 mining boost, I think. Which is pretty okay, considering it's relatively easy to grind out. And when it's charged with more Stardust, it does stuff that, yeah, I don't really think is worth it. Gives you more ores. But I'd really suggest that sometime when you have the AFK time to do it, just go grind out 2,000 Stardust. Level 6 stars should be easy enough to find, and if you're using one of the RuneLite plugins, that will help you find them anyway. Okay. So we assume the console line index is less than 80 here. Let me just actually wait. Let me go through this again to make sure I didn't screw it up. We push I, we push R0. We store A to R0. Just get it out of the way. I'm just going to go ahead and push A instead. And let me just pop A right here. That's more straightforward. Okay. Then we load the console line address, store it to I. We load the console line index. We load that from memory. We add that to I. And we store the result back to I again. Or we add I to that, and then we store it back to I again. Then, we pop A. And we store A to the console line index plus the console base address. Or the console line address. Which is not correct. We should be doing our check first to make sure that the console line index is not out of range. Because if the check is out of range, then we need to set the error flag and bail. Yeah. What are you doing with this compare anyway? I know we used to have the scroll in here, but now it does nothing. We just kind of assume the console line index doesn't get too big. Which is completely wrong. Also, we don't increment. Yeah, we do increment it, but we don't store it back out. Okay. Yeah, that's not how you do things. This whole thing is nonsensical. Okay. Instead of spending all the time calculating the address, let's just go ahead and we push R0. We pop R0 at the end. Because we're going to want to do some stuff with A in here. Okay. Been at this code for a hot minute or so. Oh, it's going to take a long time to write all this. We've written getting close to 200 lines of assembly. And we are just to displaying a character on the screen and scrolling the console. Trivial things. However, when you're dealing with it at this level, it's not trivial. I mean, it kind of is, but it also kind of isn't. Because this is, in many ways, utterly unlike anything I've ever done before, and also it isn't. It's completely like things I've done a lot. Because it didn't take me more than like an afternoon or two to write this code. And this code is sort of tested, mostly works. Written in a language I'm not terribly familiar with. I don't use very often. But it's super dense comparative to this code, which is anything but dense. Like this code, I'm going to just go ahead and write it out right here. More or less how it'd be written in a high-level language. Okay, so we want to compare our first argument. We'll call our first argument A. Oh, here. I'm just going to write out Go style. I'm going to write it out as a function. We receive an integer named A. We return nothing. Okay, first of all, if A equals 8, then we have a global variable named console line index. And we compare it to 0. If console line index equals 0, then we return. Okay. And the next thing we do, okay, we de-increment A, we push A. Wait. What are we doing here? This de-incrementing A here makes no sense. What in the hell are we doing? Yeah, that's not useful. Okay. We compare it. If it is 0, we go down to here and bail, which we did there. If it is not 0, then we push A, we push I. Okay. We have another global variable. No, this is the same one, console line index. Okay. We load the console line index. We need to de-increment this, but we can't do it up there. We need to do it down here farther. Okay. We load console line index, we store it to I. We pop A, which we pushed up here. We store to memory I. We restore A to memory. That's not right. Actually, wait. No, it is right. Because A right here. Yeah, okay, it is right. Okay. I'm being a goof. We loaded the console line index into A. Then we de-increment it. Okay. So we do A minus minus. And then we do if A equals no, we just de-increment it. We don't do an if. And then we do... No, we just do console line index minus minus. And we're done. This little tiny block of relatively easy to understand code is this block right here. A much harder to understand code. This little bit here, console line index minus minus, is all of that. And this relatively more complicated looking part is this relatively more simple looking part. So things don't translate one-to-one at all. Which makes it much harder because the code is much less readable. I guess. What it really comes down to. Also, put a little header above each of these functions so I can see where they split a little more cleanly. All right. Yeah, we've got scroll the console by one line. We've got write a single character to the console, almost done. It's more complex, but more compact. Yes and no. It's broken down into the individual tiny steps. So in some ways it's more compact because things are... you can express things in a shorter way than what the compiler would. But also it's larger because you have to take more steps to do what seems like a simple task. Okay. We've stored aside the character we want to write in R0, which we'll load up here later. Now what we want to do is we want to do LDI, console line index, LDM, A, and this will get console line index into A, the value of it. Now, we want to do DMPI 80, 1. Because we can go one pass to the end. Or, you know, we can display, no wait. It goes 0 to 80, yeah, okay, 80. And then jump 0. To place down here, we're just going to restore those registers and bail. Except we don't actually want to do that. Let's do jump not 0. We don't need to push the I register yet. We're doing it anyway. Okay. You do a lot of yes and no, and people are asking if X caliber firearm is better than Y. Well, that's just how that is. Generally, programming in any kind of assembly is going to be way harder than programming in any kind of high-level language. Because you need to understand the machine you are programming in detail. If you don't understand the machine you are programming, then you're going to have trouble and you're going to write really bad code. In this case, I understand the machine extremely well because I designed it. That makes it much easier. But that is why learning assembly nowadays in particular is quite difficult. You can learn sections of assembly pretty easily. You can learn some parts, some parts of it are just insanely complex. It's like, why would you? Somebody has to know it, I guess. Just so they can design compilers well. Anyway. Also, it's not helping me. The tools here are really crude. Partially because I wrote them myself. I'll call it this for now. Okay. If it's 0, then we just want to go straight to the end. Sort of. Like, should do jump not 0. We do GMP, boom. There we go. If it's not 0, we go just past the bounds check. If it is 0, then we do a little bit of cleanup and then we jump to the end and bail. Okay, we don't need this comparison. We've incremented A, but we do need to store it back out. So we do... Okay, we're done with the I. What does I hold? I holds an address inside the console line. Okay, yeah, we're done with I. So we do STA I, LDM I, increment A, and then we do STMI to save that result of the increment back out. And then we go through the cleanup code. Okay. Now up here we duplicate our cleanup code. And we also add a little bit more cleanup code. Namely, we want to set the error flag. So we grab the error flag. Where was I? Right here. Someday I want to write an error message out when this happens, but for now we're just going to set the error flag and bail. So we do LDI, address of the error flag, and then we do STM. Okay, we can clobber the I register here because we still saved that already. We do STAI, and we do LDI 1, then we do STM I. Yes. Okay, pop R0, pop R1. And we return. Yeah. Okay. Okay. Lots of comments so I can see what's going on. I probably should add even more comments. Some really good, well-written assembly code that I've read before literally had a comment on every single line explaining what they were doing. I'm not going to go quite that far. I'm not going to go anywhere close to that far, even though I probably should. Partially because my little address translator doesn't support comments on the same line as the instructions. And I have just realized that there's a possible bug here. That I have been subconsciously not triggering. Basically, okay. Sublime, come back here. I need you. It is in group 0, LDI, LD high. LDI. Group 0. Boom. Okay. Boot, LDA, LDI. This is not group 0. This is group 0. Okay. Boot, LDA, LDI, LD high. Okay, good. I need to double check to make sure that LDI clears the high bits. The proper order is that you load the low bits and then you load the high bits. Because if you're not setting the high bits, you need to have them cleared. And so rather than have to make you do a second instruction to clear the high bits manually, they're cleared automatically when you load the low bits. Or they darn well should be anyway. I'm just checking to make sure that there's... Yeah, because we're ORing two values together to make this work. Whereas LDI does no ORing, it just sets it. That's what we want. Just had to double check to make sure that was the way it worked. Because I caught myself a couple times. That's not what we're using. I caught myself a couple times writing LD high, LDI, load something. And then I went, no, I should do it the other way around. And I didn't really think about why. Until later. And I was like, I should go confirm that. And now I remembered to actually go do it. But yes, this is how it works. Load low, load the high. Okay, so now that we have write character done, now we need write string. Write string needs to take 2 arguments. It needs to take, well, no, it takes 1 argument. It takes a string address. And the first byte of that should be the length of the string. No. Yes. No. No. Because if I do it that way, then I'm going to have to... If I tell it to say, write a word name, I'm going to have to copy that to a buffer somewhere and do that. Yeah, no. We're just going to... Because word names are going to be bit-packed in an exciting way. I don't want to have to modify them before I write them out. So we will have 1 byte. Well, we'll have 2 addresses. Or we'll have an address and we'll have a byte or whatever. An address and a value passed in. I think I'm going to define... I should define where the character is coming from. From register A to the console. Okay. This takes no parameters, returns no values. This takes 1 parameter, returns no values, except setting the error flag, which I should also document. Okay. Write S writes a string to the console. Length is in register I address of first cell is in register A. Okay, this will make it a little easier for me. I'm also going to document what values are not preserved. I'm just going to say this clobbers A. Okay. And this will happily clobber A and I. Maybe I should just define straight up that arguments are not expected to be preserved. Hey, you know what? I'm just gonna do that. Function calls do not preserve arguments. Period. Go ahead and do full width header. Out to 120 columns. Okay. Now, length is in register I, address of the first cell is in register A, and also it's bothering me that these are all short headers. I want them to be full length headers. And I also want this to be a full length header. I'm gonna do a different style. There we go. Okay. So what we need to do is we need to call write C in a loop. The first thing we need to do is store A off to the side. So let's go ahead and push R0. And then we go STA R0. Now, we're going to do a loop. And then here at the bottom, we decrement I. And then when I equals 0, actually no, we decrement I at the top. and then we do LDA I, and then we do jump not 0 to the main loop. Okay. The reason we de-increment I is because if it contains the length, okay, we need to preserve K as well. I mean, we can't do this backwards. Because of course we can't. That wouldn't make sense. So we push K, we store A, we load 0 into I, we 0 out K, and then we do, at the end, increment K, and then we do load K into A, we compare I to A, and if they're not 0, we go back to the start. If they are 0, then we're done. We bail. Okay. Now, we do actually preserve I here. Simply by virtue of not actually using it what it's intended to be for. Maybe I should use R0 for the length instead of I. Yeah. Let's do R0. Which means we'll preserve R1 here. And we'll use R1 to store A in. Okay. Now, I just realized a problem here. Namely, LDMI and LDMK take constant offsets. That is not what I want them to do at all. And I don't know why I had them do that in the first place. It makes perfect sense for the frame pointer related stuff. It makes no sense for LDMI and LDMK. So let's go fix that up. First, let's make sure there's no cases where we're using them incorrectly in here. Boom. This should just be some simple re-encoding stuff. Yeah, it needs to be a register offset. Because the whole point of the indirect through I or indirect through K memory stores is that we can use them to implement arrays. And you want to store the base address of the array in a register. Whereas the whole point of the frame pointer stuff, wherever it is, right here. Store A to D stack indirect frame, is that you want to use this to implement local variables. And there, you're going to be using known hard-coded offsets from the frame pointer. Or you could actually use this to implement, well, no. I was going to say structures, but that's a terrible idea. Technically, you would probably want a set of load indirect instructions like this that did take immediate offsets. So you could use those for making structures. But yeah, no. You can do that other ways. Okay, so parameter is register offset. That just means we need to go flip some bits. The main thing I wanted to check though was that is group 1. Okay. Okay. Lovely. Okay. STM and LDM get constant offsets because they are fixed to 0. Because their parameters are something else. Yeah. That should be correct. Alright. Back to actual writing stuff. Oh, there's an STMI that does nothing. I should just be an STM space I. Okay. Now. In the main loop, we need to okay, R1 is the address of the first cell. We need to do, this can be annoying as hell because each cell, each memory address contains 2 characters. So we need to split them and pass them to right character one at a time. Because right character shit. Oh, I just realized right character is completely wrong. Okay. Right character is completely and utterly wrong. Also, the whole size of... No, it's not. Because this piece of crap is using 16-bit characters, I can about guarantee it. Maybe? No, there's no way. Okay, we're allocating double the amount of memory you need. That's why the characters have weird spaces between them in order to test. Okay. Yeah. We need to... Okay, if it's a new line, just scroll and build. That part's correct. If it's a backspace, delete one character. That part, looking at it again, I don't think it's correct anyway, because we don't actually zero out the character. We just de-increment the line index. Okay, we need to zero out that character. And also, the line index needs to be divided by 2 to get the actual memory address. And then, if it's a non-even value, we need to do shenanigans to set the right byte in that memory address location. We need to read it, we need to AND it with a mask, and we need to write it. And that is going to make everything be 10 times the pain in the butt that it otherwise has to be. So, I think I'm going to write a function to do this. That just takes an address, takes an index, and blindly assuming all checks have been done to make sure things are in range, does the read, write, and part. Read and write part. Maybe? Okay, this needs to take... Oops. Okay. Now, we pass the base address. We pass the offset. We pass the offset in the A register. And then we pass the base address in R0. Okay. No. Characters in A. Base address is in register I. Offset is in R0. And I don't want to do the line break there. I want to do it here. Okay. This makes the most sense because by having the base address in I, we can make use of the instructions that can deal with that. What we want to do is do LDMI A, no, R0. We need to store A somewhere temporarily. Let's just try pushing A directly for now. And we do LDMI R0. So this loads the existing value. Except that's not what we need to do at all. Okay. If it was that easy, it would be done already. What we need to do is we need to take the offset divided by 2, which thankfully is very easy to do. We don't need to do any actual division. We just do shifts. And we need to get the offset modulo 2, which is also very easy to do. We can just shift it or do a mask. Mask is probably easier. So let's get our mask set up first. I'm going to need a bunch of registers for this. Okay. STA R1. Then we do LDA 0B boom. And then we do, no wait, that should be LDI. LDI. Then we do LD high. Boom. Okay. So this gets us, actually we don't need to do LD high because it's all zeros. This gets the mask where only the first bit is set. Which we could have just done just as easily by doing LDI 1. And then we do or R0. And this gets us the first bit of R0. No, we do and, I mean. Erp. This gets us the first bit of R0. So if the first bit is set, sucks to be us. Actually, yeah, if the first bit is set, it sucks to be us. And then we do CMPI 0. Okay. Jump 0. Something somewhere. Okay. Okay, if it's 0, then we want to store it in the low byte. So set C low byte. Otherwise, you want to set it in the high byte. So if we want to set it in the high byte, we need to load no, first we have to massage R0 to be in the correct value. Let's do that above this point. No, yes, no. No. But yes. Okay, let's store A in R1. Let's preserve R0 in R2 for now. And then... No. Okay, let's temporarily make a copy of R0 and R2. And then we do... Shift left 1. Boom. And we store that in R2. Okay. What we're doing here is we're loading R0. We're shifting it left. No, we want to shift it right once. We're dividing it by 2, basically. We're shifting it right once. And then we store that result in R2. Okay. Now, that is the offset. R2 is now our new offset that we're going to use with LDMI. Okay, so in here we have to set the high byte. So we LDMI R2. This clobbers A, which thankfully we already stored in R1. And I don't think we care about the value of A right now. No. So we take... A has served its purpose by this point. But this, we take A and we... Yeah, LDMI R2. That loads the current character that is in that spot into A. And then we do LD... Shit. Okay. We do... STA. No. LDA. R1. We load our character back into A. And then we shift it 8 times. Left. Get it into the high bits. We take our 8-bit character, we shift it into the high bits. And then we LDMI. After we store our character back to R1. We STA R1, LDMI R2, then we do OR R1, take your original character that has been shifted, overlaying it. Actually, before we do that, we need to use a mask. Need to repair a mask. We can mask off the top bits before we do anything special. Just so we don't accidentally garble it. So to do that, we need to generate a mask. A is currently not used, so we can add this section right here. So we can do this. LDI, or just do LD high. No. LDI 0. LD high OXFF. No. Other way around. There. Just LDI is fine. Then we do or R1? No. Okay, we can't use R2 here. We can't use A. We can't use R1. We need R3. Okay. Now, we AND it with the mask we stored in R3 earlier. And then we OR it with R1. It being the value we loaded from memory. And then we do STMI R2 and store that result back out. Okay, that's everything we had to do to mangle the high byte. Now, to mangle the low byte, we do this exact thing again, except with a few extra steps. This time, we mask it so that we only preserve the high byte. We don't do the shift left. We can remove that whole step. So we do LDI 0. Okay, we load our mask, we store it in R3. We load our memory value. We AND it with our mask. We OR it with our character. We store it back out. Okay. I should probably add a few more comments here. Okay. And this. Okay. Now. If offset modulo 2 is not 0. Create mask to clear high byte. Okay. And then we want to Oh, what exactly are we doing here? Shift character into high byte. Zero high byte. And 4 with character. Okay. Low byte. We create mask to clear low byte. And then we their existing low byte and OR with character. And return. Okay. So set C will allow us to use a byte-based offset into an array and set the character at that byte. We're going to need a get character thing, kind of similar to this. I'm actually just going to call it set C in array. Set char in array. There we go. Oops. Okay. So we need to do let's do backspace first. Okay. So first things first, check out the backspace character. If it's not a backspace character, we bail. Then we load the console line index into the A register. We compare it to 0. If it is 0, we bail. Just return. Don't care. Okay. We probably should set the error flag for that, but we'll see if that's required later. If it's not 0, we decrement A. We push A. We push I. We load the console line index. We store the value of I in the console line index. What the hell am I doing? That is completely inexplicably wrong. No, we store A and I. Okay, that is right. Then we pop A. Can we store the value in memory? Okay, yeah. We push A, we push I. We copy the value in A to I. Or we load up something in A. And then we restore A. That's not going to work. What am I thinking? We need to pop I first before we can do that. Okay, this isn't going to work at all. Yeah, we're doing these pops in the wrong order. Unless we want to swap the values, which we don't, I'm pretty sure. Push A, push I. Load A, store A to I. Then we pop I's old value to A, which I'm pretty sure we don't want. Yeah. Let's push R0, push I. STA R0. Pop I. Pop R0. Okay, we store the value of A to R0. We load a new index into A. We store A to I. Then we LDA R0. We store it to memory in the value held in I. This is completely wrong. I'm just going to delete all of this, I think. No, well, I'll start over from the beginning, but I'm not going to delete it until I'm sure. Okay. This part fairly sane. We'll load the console line index into A. Compare it to 0. Boom. Okay. Now, what we want to do right here is we want to de-increment the console line index by 1. And then we want to call setchar an array. Okay. And we need to preserve the RTN register around that. Okay. So call setchar an array. This uses the A register, the I register, and R0. So we need to preserve those two. Possibly not the A register. We definitely need to preserve R0 and the I register. Okay. Now, currently, the A register holds the value of console line index. We need that offset to be in R0. So, we do STA, R0, increment R0. And then we do the magic to... Okay, now we have the actual offset we want to write to. Or the offset we want to clear. In R0. So let's clear that offset, or let's store this offset first while we still have it. Because we're not going to assume set char to array preserves it, because that is convention. We could just scroll up and look at it to make sure it preserves it. I'm pretty sure it does, but I don't... Yeah, we're not going to trust that that's going to remain that way forever. That's why you have calling conventions. And other convention things like that. You don't have to go look at the code to assume it's going to be a certain way, because you write all your code to be that way. And if you don't, I pity you. Okay, so we need to do LDI, console line index, then we do actually, if we don't store A to R0 yet, we decrement A. No. Because we need to do this LDI here. Okay. We need to get an address into a register somehow. We've got it in A register now. It needs to be a not A register so we can load R0 into A. What registers do we have available? We've got I available. We're preparing to collaborate. Okay. We do STAI. And then we do LDA R0 STM I. And this will store R0 to memory at the index indicated, or at the address indicated by I. Now, R0 is properly set. A and I are probably not. No, we need the base we need the base address in I. To get the base address, we need to do this. Console line low to LDI with LDI, console line high with LD high. Store that in I. Then A is the character we want to write. So for that, we just do LDI 0 because we're clearing it. We're just going to set it to the null character. We could do 32 and set it to space, but we're setting it to the null character. Then we call set char an array. And when we're done, we pop I, pop R0, pop RTN, and return. Okay. Yeah. That's a lot of bullshit to get backspace to work. Most of this bullshit is going to be down here as well. So, push I, push R0, store A to R0, So far, so boring. We need to increment R0 this time. Let's just comment the hell out of this while we're thinking about it. If backspace, delete one character. Okay, checking if it's backspace. Make sure console line index is greater than 0. Okay. Observe registers, that's not interesting enough to comment on. Okay. Wait, what am I doing that for? Oh. That's not what we're doing there at all. Okay, this is doing... This is getting the address of console line index into I. And this is getting the value. Yeah, okay. Now. Okay. And then we go ahead and okay. Easy enough. Not really, but... Okay. Write the character to the line, assuming it's ASCII. So, we push I. We push R0 just to store them. Preserve them. We're going to be using set char and array, so it's also push RTN. You know what? Let's just copy our existing preamble and PostScript. Okay. Now, go bounce check. We load console line index into A. Compare it to 80. If it's not 0, we bail. If it is 0, then we do stuff. Namely, we set the error flag. And return. Now, it's not out of bounds. So, we load the base address to I. We load the console line index. Okay. We need to increment it. We need to store the character and then we need to increment it. Fun. So this part is probably going to be wrong. Okay. We load and set I. Where did we store our character? We didn't. Okay. We need to do STA. R0. Okay. We don't need to preserve A because we don't need to actually do LDAR0 here. Because it's an argument and we don't preserve arguments. LDAR0 here. And I just realized R0 is a terrible place to store that because R0 is one of the arguments we need to pass. We need to pass the offset in R0. Okay. So we will store it in R1. Means we need to preserve another register here. Okay, and here we need to load our offset, which is console line index. Console line index will be an A at this point. Right here. So we can do STA R0. Then we call set char an array. Now, we also have a little bit of an issue here, namely that we did not preserve that value. So we will load it from memory again. LDI, console line index, LDM, A, increment, A, and then we want to do STA R0. Then we do Load that address again. Store A to I. Load A from R0 again. Store it to memory. And then restore everything. Okay, good deal. That should be correct. Almost 300 lines. And all we've got to show for it is hopefully non-buggy code. The right characters to the console. One character at a time. I'm tempted to test it, but I'm about guarantee you it's going to blow up in spectacular fashion. Okay. What arguments does this use? Just write a single character from A to the console. Okay. All right. So here we push R1, we push K, we store A in R1. Sensible. Like, why didn't we just use R1 as a parameter in the first place? That way we have the guarantee that R1 is preserved externally. A is going to get clobbered pretty much no matter what happens, so we can just always assume that A isn't preserved and be happy. So we always want to use A as one of the parameters. Mostly. That's just some strong reason not to. Also, using A as a parameter gives us the greatest flexibility, because A is the most versatile register. It can store it anywhere. So we store A to R1. We load 0, we store it to K. We zero out K, basically. And then we enter a loop where we're going to be incrementing K, pairing it to R0, which is where the length is stored. Okay, very simple. The loop part is done. However, the length is in I just realized I think I know where we have a bug. Maybe not. There's a possible bug here where this value is 1 too low. Maybe? Think about it. We're more likely to have to test it than wonder why it breaks. Ugh. We might need to use offset divided by 2 plus 1. I'll just leave a note there for myself, so if I encounter a weird bug, I will have some idea of what it might be. Okay. So here we need to do a lot of the same things we would need to do what we did earlier. We need to split cells. So we need to divide, and then we need to basically use division and modulus to figure out what the actual offset is. Inside the loop. So the way to do that is not to compare to R0. We want to compare to R0. Ah, shit. We need a couple more registers for sure. Okay. Then we do OR1, STA, R2. This is length modulo 2. We do and 1. Derp. Did I definitely do and up here? Yes. Okay. And then we do length divided by 2, which is going to be LDA R1. And then we do shift right 1 base. Then we do STA R3. Okay, so R2 is length modulo 2, which is going to be 1 or 0. And STA is length divided by 2. We want to use compare R3 inside the loop. Because we don't want to loop half as many times. And this is going to pain in the ass. We need to call write C twice. Let's do high and then low. This could be backwards, in which case it'll garble the string, but that's easy enough to fix. So what we will do is LDM. Okay, so at the top of the loop, we need to load our memory location. We need to do LDMK. R1. I just realized we did this wrong. This should be R0. what am I doing here? Oh, I'm zeroing out K. Here I'm... Okay, there we go. We need to work on R0, not R1. Because R1 is the address of the first cell. R0 is the length. The value we actually wanted to do modulo and divide. Okay. R1 now contains the address of the first cell. We want to do LDMK R1, where the address is in R1 and the offset is in K. Technically, you can put the address in K and the offset in R1. It works either way. But this is how we're doing it. Because this is the way that makes the most sense with a loop. Now, technically it makes perfect sense either way because we can use the increment instruction either way. The only special meaning that I and K have is with the LDMK and LDMI, STMK and STMI. That's beside the point though. And the point is that we are loading memory starting at R1. R1 plus 0. And going up to R1 plus length minus 1. Well, R1 plus length divided by 2 minus 1. Which, now that I think about it, is probably too short. It should be length divided by 2. Probably. Anyway. Plus possibly 1/2. I think it needs to be length divided by 2 plus 1/2. Which we're not doing. And we will need to do later. Probably. If it breaks, it breaks and we'll know. As long as we always give it even length strings, it'll work no matter what. Not a reasonable expectation. Okay. LDMK R1. So that loads the pair of characters we want to write into A. R1, R2, and R3 are all busy. So we're going to need R4. I'm using a lot of registers here. Okay. What we need to do at this point is we need to take the value in A and we need to split it in half. We need to mask off the high bits and get the low bits. And we need to mask off, or we need to shift away the low bits. So, let's shift away the low bits first. First of all, though, let's store A in R4 so we can access it later. And then we will shift right 8. And then we'll call write C. Oh, we need to store return as well. Because we are calling functions inside here. Okay. Now, the next half, we do LDA R4. And then we do... Actually, no, we don't do LDR8. Damn it. I need yet another register. Store the mask in. Yeah, because I can't use a constant mask or anything. Okay, R5 it is. Let's use all the registers. There might be another register that we already have saved in here, but yeah, moving on. Okay. Now we do LDI 0. No. Actually, we could use... Yeah, it doesn't matter. We need a register for this anyway. OXFF. STA. R5. And R5. After doing LDA R4. Not before. And this will get us a value in A that has none of its low bits set. Okay. And then we're done with the loop. Okay, let's find out if any of this bullshit even slightly works. Okay. Calling convention for write S is length and register R0, address of first cells and register A. Okay. Let's go ahead and build a string. LDI. I should have... built some code into my little transpiler thing to handle character constants. That'd make my life so much easier. Oh well. I don't have character constant support, so I'm going to... or yet, anyway. So I'm going to have to go back and call upon the power of the ASCII table. Okay. 65 for A. We're just going to do a really short basic string. Okay. There. We'll have a couple of scroll operations in there. This probably isn't going to work, just so everyone knows. Okay. We can't use addresses starting from 0. We'll use addresses starting from 100. With plenty of space. Okay. Here. There's no reason to put these on separate lines. In the brain-breaking game, you're starting to miss it. It's not that bad. Come on. We've been playing Meta, the brain-breaking game, today. Okay. "11 characters. Okay. We need to store that into register R0. And then we need to load the beginning address, which we hopefully know because I hard-coded it. Go me. And we can call write string. And this should write ABC. Boom, 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 like that. And scroll each time. Okay. It probably won't. To be perfectly clear. Okay. Just scroll through the output real quick and see if anything incredibly obvious is broken. Doesn't look like it. I mean, there's some stuff that's wrong, but anyway. It's in comments, so nobody cares. Damn it. Okay. Why is it constantly running without incrementing the... Oh, I see what the problem is. Yeah. No, it just looked like it was doing the wrong thing. Okay, it's loading values into memory. Right here. And it's not doing it correctly at all. Because of course it isn't. Okay. We want to do increment I every other time. Okay, screw it. No, we can't delete that. Okay, I need to go fix this in the actual editor because if I don't, it's going to be completely wrong. Wronger than it already is going to be. Because it's going to throw off all the offsets throughout the whole file. You can't really edit things in that editor. Okay. Every other one needs to be an LD high. Okay. Run the processor again. It is indeed loading stuff correctly, it looks like. Doing something. And it's back to loading again. Okay, what is this problem? Okay, so I called into write string. Here we go. Why did it go back to the beginning instead of calling write string? OXB4, OX80. Okay. Let's stop it when it gets here. So it loads the string into memory. All right. It's now ready to call write string. Which I already checked function calls work. I confirmed it with a simpler, much simpler program. Damn it! Did I just destroy? Yes, it did. Free. Okay. Takes forever to get to this point. Okay. So at this point, it should be loading the instruction. Boom, there just executed LDI. Now it's loading call. Boom, it's executing call. Okay. It should (32948) 32948. Okay. That's writing into the... Okay. So B4. That would be 32. Let's just type it in. 180. We're going down to instruction 180. No, we're not. We're going down to 100 instruction 180 times 2. So 360. Boom, right here. 360. Right at the start of write string. Okay. Now, the next thing that should run is this. Except it isn't. It runs return. And return resets to 0 because the return register is 0 right now. Why is it 1 off? It wasn't 1 off in my tests. Interesting. We could change this to B5 and it would probably work. But then, what other ones would break? Are all of them 1 off? That doesn't make any sense because I tested function calls as working. Is it not? Interesting. Well, I need to figure out why that's happening. Because if I can't trust it to jump to the right place, we have an issue. And it's a hardware issue in this case because the software has nothing to do with, well, I want to check something here. Okay. 361 is the offset at the beginning of this. Is it? That doesn't make any sense. Why is it giving us an odd... Okay, this one's 0, this one's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 60, 62, 68. Where's the first one that goes uneven? 127. Oh. There's a jump not 0 here that doesn't have its gummy instruction on line 118. Okay, that would do it. Okay. Let's just run our little screwed up jumps searches. Okay, we didn't find any more screwed up jumps. Whereas if we delete that, boom, we immediately find one. Alright. Run the program again. We don't want the input file, we want the output file. Game is running like absolute shit while it's doing the simulation. What the hell? Oh yeah, that's of course. Let's scroll down where we actually enter write string. And let's just execute it until we get there. Boom. Okay, this time we actually did jump into write string. Good deal. Well, let's just let it go. Short circuit. Okay, what instruction were we even running? This is an interesting issue. Okay, this bit decoder and that diode. Oh, I need a diode here. Maybe? No. There's two people trying to write PC at once. Writing PC? That's not PC. This is PC. Stack, stack. Oh, they're writing the return register. What? Who's writing the return register? Okay, what instruction is being decoded? 50? Okay. That'd be group 2. Instruction. Hmm? That doesn't make any sense. That'd be a pop. Why would pop be trying to... Yeah, it's all lit up in here. That's just simple pop. But why is this doing anything when pop is live? It's not. This 3-bit decoder is outputting nothing. Okay, yeah. It is definitely a case of needing a diode. Okay. Okay. Yeah. Because this is forcibly set low. Okay. I see. Let's try that again. My frame rate. Not outputting anything on the screen yet. It is hooked up. Okay. It definitely should have output something by now. And the fact it didn't makes me believe that I have a bug somewhere. Yay! It's definitely running code. I just need to figure out where it's running code. Okay, let's go find the pretty blue line. Okay, it is in... right C. Okay, now it's calling set char and array. Boom. Where'd it go? There it is. Here's the low byte. Sets it, returns it. Okay. You're back here down now again. Okay, so it clearly thinks it's doing something, but it's not displaying on the screen. It hasn't crashed, it's just not doing what it's supposed to do. I'm not sure where it's actually writing, is the problem. but it's doing something. It's stuck in a loop? Possibly not. It's only in the low hundreds of ticks. Not quite thousands, or high hundreds, I guess I should say. Okay, just hit set char and array. Now it's back from set char and array. And off it goes again. We should see at least a couple scrolls, which could take a significant amount of time. It just doesn't seem to be working. And I don't know if it's because I'm writing to the wrong... Oh, part of it's probably because I'm writing to the wrong spot. Yeah, I never did fix those offsets. You know what? I'm writing to the wrong part of memory. I'm not. I didn't fix the offsets for the stacks. I don't think. Or did I? No. So the console buffer is way larger than it has to be. But that's fine. We only care that the start of the console buffer is at the start of the console buffer. Oh, no we don't. Because this is at the end of the console buffer. That's right. I need to fix those do offsets. That's why it's not displaying anything. Okay. So we need 1200 here. Decimal. Clear. 1200 minus 80 divided by 2 plus 768 equals 0530. That's not right at all. I did divide it by 2 at the wrong stage, I think. No? What? Okay, here. Clear it all. Okay. Yeah, no, that's right. 05. Three zero. Now, just run our little transpiler. Copy the output. Start it running and watch the console. Hopefully, it starts to work. The output should appear in the bottom corner here. However, it is not yet. There we go. not showing up the right spot, but output is showing up, which means we are copying bytes to memory. Very slowly and inefficiently, question mark. Why did it do A, B, A? It's supposed to... not do that. That's what it's not. What's supposed to do. Okay. It is very definitely confused about its job. A, B, A, C, space, C, D, E. That's not what it's supposed to do. It's supposed to do ABC, scroll to a new line. CBD, scroll to a new line. DED, scroll to a new line. Or not DED, whatever. ABC. Whatever. It's not doing the right thing. And I do not have time to debug it anymore tonight, because it is 11:30 almost. So, debugging string output in the Shin 16 will have to be accomplished tomorrow. Hopefully we can get string output working reliably and move on to some more interesting things. I have to admit, this is going a little bit slower than I had originally planned. Although I should have easily foreseen just how long this is going to take. Because, well, I knew what I was getting myself into. It's just that overconfidence strikes again. We'll just have to keep grinding away at it, and eventually it'll work. Hopefully. The interesting thing, though, is that we are capable of running much more complicated programs on it than what we were before. That is for sure. Oh, let's see, who's doing what tonight? Nobody is doing anything. That's what they're doing tonight. Wow, what a boring bunch. I need to get some more people on my follow list, apparently. I guess we won't raid anybody then. Yeah, tomorrow, hopefully we can get the bugs hammered out relatively quickly and get the string output functions working, get console scrolling working. And once those are running, then it will be a matter of slamming our head repeatedly against other bits, namely string input. And once I have keyboard input running, then we have everything we need to start doing really basic, a really simple read, evaluate, print loop. And with that, we can start working our way toward a fourth system, and eventually a fourth system with an integrated assembler. Because that is the thing that people used to have for old systems like this, or, you know, more limited systems like this. Fourth actually lends itself really well to having integrated assemblers. But anyway, that's enough rambling for one night. We can ramble more about my plans tomorrow. Until then, I hope you all have an awesome night. And I will see you all later. Good night. And goodbye.